Imagine a universe that didn't just burst into existence with a bang, but instead slipped through an impossible barrier, appearing as if by magic. It's a mind-bending thought, isn't it? For decades, we've been captivated by the idea of the Big Bang, a moment of cosmic inflation that created everything we see around us. But what if that wasn't the absolute beginning? What if before that monumental expansion, the universe underwent something even stranger, something that defies our everyday intuition? This is where the incredible, almost surreal concept of the universe's very first quantum tunneling event enters the picture. We're talking about a phenomenon so bizarre that it seems ripped straight from science fiction, yet it's a fundamental part of how the universe works at its most microscopic level. Quantum tunneling allows particles to quite literally pass through solid walls or impenetrable barriers, not by blasting a hole, but by sort of dematerializing on one side and reappearing on the other. It's like walking through a brick wall without touching it. Now, scale that up to the earliest moments of existence, to the conditions that were so extreme, so unlike anything we can currently observe, that our standard understanding of physics starts to unravel. Could this fundamental quirk of the quantum world, this ability to tunnel through the impossible, have played a role in the universe's birth? What if, instead of a traditional beginning, the universe tunneled into existence from a state we can barely comprehend? This isn't just a philosophical musing. It's a question at the very frontier of cosmology and quantum physics, a mystery that challenges scientists to think in entirely new ways. It forces us to confront the possibility that the reality we inhabit emerged from a point where the rules we know no longer applied, where the impossible became possible through the strange and powerful mechanisms of quantum mechanics. The implications of this idea are truly profound, reshaping our notions of what reality is and how it all began. It suggests that the universe might have originated not in a singular, explosive event from nothingness, but from a transition, a quantum leap from one state to another, bypassing seemingly insurmountable obstacles. The very idea that the universe could have quantum tunneled into being opens up a realm of incredible possibilities and fascinating questions. It's a concept steeped in mystery, pushing the boundaries of theoretical physics and inviting us to explore the deepest secrets of existence. For over a century, scientists have grappled with the strangeness of the quantum world, and now they are applying its principles to the grandest stage imaginable, the birth of the cosmos. This journey isn't just about understanding the past, it's about redefining our present and fundamental future. As we delve into the various theories proposed to explain this cosmic tunneling event, we'll touch upon concepts that sound like they belong in speculative fiction, but are seriously considered possibilities by leading minds in the field. These are ideas that challenge our intuitions about time, space, and the very fabric of reality. Get ready to have your mind expanded, because we're about to explore 30 fascinating theories about the universe's very first quantum tunneling event, each offering a unique perspective on the most momentous transition in all of existence. It's a journey into the bizarre, the beautiful, and the utterly mind-bending, promising insights that will leave you looking at the sky, and perhaps at reality itself in a completely new light. One compelling idea on the table is called the inflationary tunneling model. Now, you've likely heard of cosmic inflation, that incredibly brief period right after the Big Bang where the universe expanded exponentially, stretching from something smaller than an atom to astronomical sizes in a fraction of a second. This inflationary phase is generally accepted by cosmologists because it neatly explains some of the biggest mysteries left unanswered by the standard Big Bang picture, like why the universe looks so uniform on large scales and why space appears flat. But the inflationary tunneling model takes things a step further. It proposes that even before inflation kicked in, the universe wasn't in a state we would recognize. Instead, it might have existed in a kind of metastable vacuum state, a precarious energy level where it was trapped. Think of a ball sitting in a small dip on a bumpy surface. It's not at the absolute lowest point, but it needs a push to get out. In this model, that push came from a quantum tunneling event. The universe simply tunneled out of this trapped state, bypassing a potential energy barrier it couldn't classically overcome. This tunneling event wasn't just a random fluctuation. It's thought to have been intricately linked to the very field that powered inflation, the inflaton field. This hypothetical field, permeating early space-time, is theorized to have been responsible for the initial tunneling and then, as it settled into a lower energy state, for the explosive inflationary expansion that followed. This model offers elegant solutions to some of cosmology's stubborn problems. The horizon problem, for instance, asks why distant parts of the universe that should never have been in causal contact look so similar in temperature. Inflation solves this by saying these regions were in contact before rapid expansion pushed them far apart. The flatness problem questions why the universe's geometry is so close to being perfectly flat, a very unlikely scenario without some driving force. Inflation stretches any initial curvature flat. The inflationary tunneling model provides a mechanism for how inflation itself could have been triggered, suggesting it arose from a quantum leap into a new state driven by the inflaton field. Prominent figures like Andre Linde have been key proponents of inflationary theory, including the tunneling idea as a potential starting point for the inflationary epoch. While directly observing the conditions of the very early universe remains a profound challenge, the inflationary tunneling model makes predictions that are being tested against data from cosmic microwave background radiation, the afterglow of the Big Bang. Patterns in this radiation, if they align with the predictions of inflationary models, lend support to the idea that inflation happened, and by extension, to the possibility that it was initiated by a quantum tunneling event from a previous state. It's a picture of the universe not being born from nothing, but from a transition, a quantum jump out of a primordial state, powered by a field that then drove the universe to inflate to the vastness we observe today. Another theory that truly stretches the mind proposes that the universe didn't tunnel from some pre-existing state, however strange, but actually tunneled into existence from nothing. Now, when physicists talk about nothing in this context, they don't mean just empty space like a vast void. In quantum mechanics, even what we perceive as empty space is a buzzing hive of activity, particles constantly popping into and out of existence in what are called vacuum fluctuations. But the nothing in this theory is even more radical than that. It's a state without even classical space-time, a realm utterly devoid of the dimensions and fundamental ingredients of the universe as we know it. Imagine a point where there's no before and no after, no here and no there. This theory suggests the universe emerged from this absolute quantum nothingness through a spontaneous tunneling event. It's like a bubble of reality quantum tunneling into existence from something that wasn't even a bubble, but a void beyond our current understanding. This idea is deeply rooted in quantum cosmology, a field that attempts to apply the principles of quantum mechanics to the universe as a whole, especially its very origin. Mathematical frameworks within quantum cosmology suggest that it's theoretically possible for a universe with complex features like matter, energy, and space-time to arise from a state of absolute simplicity or perhaps absolute non-existence in a classical sense. The equations seem to allow for this possibility, suggesting that the creation of the universe could literally be a quantum event on the grandest scale imaginable. Think of a potential energy landscape, but instead of particles tunneling through a barrier, it's the entire universe tunneling from a state of zero size and energy to a state where space-time exists and inflation can begin. The philosophical implications here are immense and have sparked considerable debate. If the universe arose spontaneously from nothing through a quantum process, does that mean it doesn't require a prior cause? This challenges deeply ingrained ideas about causality and creation, forcing us to confront the possibility that the most fundamental event of all might have simply happened uncaused. The debate also circles back to that definition of nothing. Is it truly nothing, or is it a different kind of nothing, a quantum vacuum state that exists beyond our classical understanding? Prominent physicists have explored this theory. Stephen Hawking, in his later work alongside Thomas Hertog, explored the idea of a universe that began with no boundary condition, implying a spontaneous quantum origin. Alexander Vilenkin of Tufts University has also been a strong proponent of the universe tunneling from nothing, developing models that support this possibility. He famously put it that the probability of the universe tunneling from nothing is not zero. It's a powerful statement suggesting that our entire reality could be the result of an incredibly unlikely, yet fundamentally possible quantum fluctuation in the ultimate void. This theory paints a picture of a universe that is, in a profound sense, self-creating, arising from the deepest level of quantum possibility. Shifting gears a bit, another mind-expanding theory suggests that our universe isn't the only universe, but just one bubble in an unimaginably vast and perhaps infinite collection of universes, a concept known as the multiverse. In this scenario, the birth of our universe wasn't an isolated event standing alone in nothingness, but rather a tunneling event that occurred from a parent or neighboring universe. Imagine our universe as just one soap bubble forming and detaching from a larger, perhaps eternally inflating sea of bubbles. This model often ties back into certain versions of inflationary theory, particularly a concept known as eternal inflation. In the eternal inflation picture, the process of inflation doesn't stop everywhere at once. Instead, it continues indefinitely in some regions while ending in others. When inflation ends in a particular region, that region pinches off and becomes a separate bubble universe. Our universe, according to the multiverse tunneling hypothesis, could have formed when one of these inflated regions underwent a quantum tunneling event, transitioning from the inflating state of a parent universe into the distinct, expanding universe we inhabit. The conditions in the source universe that could trigger such a tunneling event into our own are a subject of intense theoretical speculation. One idea is that fluctuations in quantum fields within the parent universe reached a critical point, providing the necessary conditions for a new vacuum state, the state of our universe, to tunnel into existence. Picture it like a phase transition, similar to how water turns into ice, but on a cosmic scale and driven by quantum rules. Small fluctuations in the energetic landscape of the parent universe could, against all classical odds, allow a pocket of a different, lower energy vacuum state to spontaneously appear and then rapidly expand into our own universe. The idea is that the parent universe provides the underlying space-time fabric and quantum fields from which our universe could emerge via tunneling, rather than our universe appearing from absolute nothingness. Now, exploring the multiverse tunneling hypothesis presents significant challenges. The most obvious one is testing it. By definition, different universes in this model are largely separated and unable to interact with each other. This makes direct observation of a parent or neighboring universe seemingly impossible with our current technology. How do you gather evidence for something you can't see or touch? This leads to considerable debate within the scientific community. Is the multiverse a testable scientific hypothesis, or is it more of a philosophical concept? Some physicists argue that while we can't directly observe other universes, the predictions made by theories that include a multiverse could potentially be tested. For example, theories involving bubble universe collisions might leave detectable imprints in the cosmic microwave background radiation, though finding such definitive evidence is incredibly difficult and highly debated. Others remain skeptical, arguing that a theory that cannot be falsified through observation or experiment falls outside the realm of empirical science. Despite the challenges, the multiverse tunneling hypothesis remains a compelling avenue of investigation because it arises naturally from certain well-motivated cosmological models, especially those involving eternal inflation. It offers a potential explanation for why our universe has the specific physical constants and properties it does. Perhaps we simply live in one of the bubble universes where these conditions are suitable for life to arise. While the visual of bubble universes expanding and potentially colliding is striking and helps illustrate the concept, it's important to remember that these are highly theoretical ideas, pushing the very limits of our understanding of reality. The possibility that our universe is just one of many, born from a quantum tunneling event within a larger cosmic structure, is both humbling and awe-inspiring, a testament to the strangeness and vastness of what might lie beyond our observable reality. Delving even deeper into the quantum weirdness, some physicists propose that the universe emerged not from a pre-existing state or even absolute nothingness in the classical sense, but from a chaotic, turbulent realm at incredibly small scales known as spacetime foam. Imagine looking at the fabric of reality, the smooth expanse of spacetime we experience every day. Now picture zooming in, way in, past atoms, past fundamental particles, down to the Planck scale, an unimaginably tiny size around 10 to the power of -35 meters. At this scale, quantum mechanics reigns supreme, and the traditional smooth picture of spacetime might break down entirely. The spacetime foam theory suggests that at these microscopic levels, spacetime isn't a flat sheet, but rather a chaotic, boiling sea of quantum fluctuations, tiny regions of spacetime constantly popping into and out of existence, wormholes briefly forming and disappearing, a veritable foam of fluctuating geometry and topology. It's a state where gravity and quantum mechanics are intrinsically linked, and the very structure of reality is in flux. From this turbulent, foamy background, the theory posits that a particularly significant and sustained fluctuation, a sort of larger-than-average instability in the foam, could have quantum mechanically tunneled into the initial conditions of our smooth, expanding universe. Think of it like a particularly large wave appearing in a stormy sea, but instead of just cresting and falling, this wave somehow transitioned into an entirely different state, becoming the stable, expanding universe we inhabit. It's a concept deeply intertwined with the quest for a theory of quantum gravity, a theoretical framework that can successfully merge Einstein's general relativity, our best description of gravity on large scales, with quantum mechanics, which governs the universe at its most fundamental level. Because the extreme conditions of the early universe, particularly at the moment of its birth, involve incredibly high energies and incredibly small scales where both gravity and quantum effects are significant, understanding this spacetime foam is crucial to formulating a consistent picture of cosmic origins. The energies involved in this proposed tunneling event from spacetime foam are utterly staggering, far beyond anything we can replicate in laboratories. We are talking about conditions where the very fundamental constants of physics might behave differently, and spacetime itself might have a structure we can barely conceive of. Researchers in string theory and loop quantum gravity, two prominent candidates for a theory of quantum gravity, explore the characteristics of spacetime at these fundamental scales and investigate whether such a tunneling event from a foamy state is a plausible outcome of their theoretical frameworks. While directly observing this Planck scale foam is currently impossible due to the extreme energies required, the mathematical consistency and predictive power of theories describing it are what scientists are scrutinizing. If a theory of quantum gravity successfully predicts observable phenomena in the universe today, it could offer tantalizing indirect evidence that the universe indeed emerged from a state of spacetime foam via quantum tunneling. This theory paints a picture of our universe not emerging from empty space, but from the very stuff of quantum gravity itself, a turbulent, probabilistic realm giving rise to the ordered, expanding cosmos through a monumental act of quantum tunneling. Moving on, consider a different theoretical landscape where quantum tunneling might play its part in the universe's origin, the realm of loop quantum gravity, or LQG. This is a fascinating alternative to string theory in the quest for quantum gravity, a theory that seeks to unify general relativity with quantum mechanics. LQG paints a radically different picture of spacetime at the most fundamental level. Instead of a smooth, continuous fabric, LQG suggests that spacetime itself is quantized, meaning it comes in discrete, indivisible chunks, much like energy is quantized in quantum mechanics. Imagine spacetime as being woven from tiny, interlinked loops or networks, creating a sort of quantum tapestry. These loops are incredibly small, existing at that same Planck scale we discussed earlier, far beyond our current observational capabilities. The geometry of spacetime, according to LQG, isn't defined by a smooth manifold but by the intricate connections and configurations of these quantum loops, forming what's sometimes called a spin network or spin foam. Now, how does quantum tunneling fit into this loop quantum picture? LQG offers a compelling scenario for the universe's beginning known as the Big Bounce. In standard general relativity, if we trace the universe's expansion backward in time, we reach the Big Bang singularity, a point of infinite density and curvature where the laws of physics break down. Similarly, if a universe were to collapse in on itself, it would end in a Big Crunch singularity. LQG attempts to resolve these singularities. Within the framework of LQG, the quantization of spacetime prevents the universe from ever actually reaching infinite density. As a collapsing universe shrinks, the repulsive force of quantum gravity, which becomes significant at extremely high densities and tiny scales, would eventually halt the collapse. Instead of hitting a singularity, the universe would literally bounce back out into a new phase of expansion. This transition from contraction to expansion is where the quantum tunneling concept potentially comes in. The Big Crunch singularity that general relativity predicts is effectively a barrier in the gravitational landscape. A classically collapsing universe would be trapped at that singularity. However, in LQG, the quantum nature of spacetime allows the universe to potentially quantum tunnel through this predicted singularity into a new, expanding phase. It's not a classical bounce where it hits something and rebounds. It's a quantum leap through a barrier that classically shouldn't be passable. The universe doesn't touch the singularity. It transitions past it via tunneling, emerging into a new cycle of existence. The resolution of the singularity problem is one of the most significant achievements claimed by LQG. By quantizing spacetime, the theory provides a framework where the densities and curvatures remain finite, even at the point of maximum compression during the bounce. The concept of the Big Bounce, facilitated by quantum tunneling through the singularity barrier, offers an alternative to the universe originating from nothing or from a pre-inflationary state in the standard model. It suggests our universe might be part of an endless cycle of expansion and contraction, with each bounce being a quantum tunneling event through the point of maximum compression. While directly observing the spin network structure of spacetime or the quantum tunneling event of a Big Bounce is currently impossible, theorists are exploring ways to look for subtle imprints of LQG and a possible Big Bounce in the cosmic microwave background or in the distribution of galaxies. The search for these observational signatures is a key part of testing whether LQG and its Big Bounce scenario, powered by cosmic-scale quantum tunneling, represents the true nature of the universe's origin. Consider a fascinating theory known as tunneling from a false vacuum. This idea suggests that the very early universe wasn't in the lowest possible energy state. In quantum field theory, the vacuum isn't empty, it's filled with quantum fields, each with an associated energy level. The lowest energy state is called the true vacuum. However, sometimes a system can get stuck in a higher energy state that still looks stable, like a temporary dip before the lowest point. This is called a false vacuum. Imagine a ball sitting in a shallow dent at the top of a hill. It's stable there for a while, but the true lowest energy state is at the bottom of the valley. The false vacuum theory proposes the early universe was like that ball, trapped in a potentially very high energy false vacuum state. For the universe to get to its current state, which is believed to be a much lower energy true vacuum, it would need to transition out of this false vacuum. Classically, to leave the false vacuum, get the ball out of the dent, you'd need to push it over the hill. But in the quantum world, a phenomenon called quantum tunneling allows the universe to bypass that energy barrier entirely. The universe, in the false vacuum state, could spontaneously tunnel through the energy barrier, separating it from the true vacuum. When this tunneling happens, it's not a gentle slide down the hill. It's a dramatic release of the enormous energy stored in the false vacuum. This burst of energy would then fuel a rapid expansion of the universe, potentially triggering that period of inflation we discussed earlier. This transition from a false to a true vacuum state via quantum tunneling is envisioned as a powerful cosmic transformation, fundamentally reshaping the universe. The conditions required for such a tunneling event are extreme, involving incredibly high energy densities. It wouldn't happen everywhere in the false vacuum simultaneously. Instead, it would likely start in a small region, a bubble of the true vacuum spontaneously forming within the false vacuum. This bubble would then expand, converting the surrounding false vacuum into the true vacuum and releasing energy as it goes. The rate of this tunneling depends on the height and width of the energy barrier between the false and true vacuum states. A higher or wider barrier means a lower probability of tunneling and a longer expected lifetime for the false vacuum. Conversely, a lower or narrower barrier makes tunneling more likely. The consequences of tunneling from a false vacuum could be profound and potentially observable. If the transition didn't happen uniformly, the expanding bubbles of true vacuum could collide, potentially forming topological defects called domain walls. These domain walls are interfaces between regions that originated from different true vacuum bubbles. While cosmologists have searched, they haven't found evidence for these domain walls in the current universe, which places constraints on the parameters of any false vacuum tunneling scenario. Another consequence, and perhaps the most significant, is that if our current universe is in a true vacuum state that was reached via tunneling, it raises the question of whether our current vacuum is truly stable or just a very long-lived false vacuum. Could our universe eventually undergo another tunneling event to an even lower energy state, with potentially catastrophic consequences for the existence of structures within it? This idea, known as vacuum decay, is a serious topic of discussion in theoretical physics, highlighting that even the seeming solidity of our reality might be a temporary phase in the grand cosmic evolution driven by quantum probabilities. It forces us to consider the surprising fragility that can arise from quantum processes on a cosmic scale. Delving into even more abstract territory, some theories propose a profound connection between the universe's initial quantum tunneling event and the very origin of the arrow of time. We experience time moving forward from past to future, an irreversible progression. This is known as the arrow of time, but the fundamental laws of physics at their deep core are largely time-symmetric. They work the same whether time runs forward or backward. So, where does this perceived directionality of time come from? One powerful explanation lies in thermodynamics and the concept of entropy. The second law of thermodynamics states that the total entropy of an isolated system can only increase over time, meaning that systems naturally tend towards disorder. The universe started in a state of incredibly low entropy, meaning it was highly ordered. As it evolves, entropy increases, and this progression from low to high entropy provides a direction for time, the thermodynamic arrow of time. Now the question arises, why did the universe start in such a low entropy state in the first place? This is sometimes called the past hypothesis, a fundamental assumption in cosmology that seems necessary to explain the arrow of time we observe. This is where quantum tunneling enters the discussion in a fascinating way. The probabilistic nature of quantum tunneling, that inherent unpredictability of when and where a particle might tunnel through a barrier, is inherently tied to processes that break time symmetry. Unlike classical physics, where outcomes are determined by initial conditions, quantum mechanics introduces a level of randomness and irreversibility into fundamental processes. Some theoretical frameworks suggest that the very act of quantum tunneling that brought our universe into existence could have been the crucial event that broke the time symmetry inherent in the fundamental laws, thereby establishing the initial low entropy state and setting the stage for the arrow of time we experience. Imagine the tunneling event as a spontaneous transition from a state where time might not have had a defined direction or where it was symmetrical, to a new state, our universe, where time began to flow irreversibly forward due to the newly established low entropy conditions. Consider how a system in quantum mechanics evolves. Its state is described by a wave function which evolves deterministically according to the Schrödinger equation, a time-symmetric equation. However, when a measurement is made, the wave function collapses into a specific outcome, a process that appears to be inherently irreversible and non-deterministic, introducing an arrow of time at the quantum level. Similarly, the spontaneous, probabilistic nature of the universe quantum tunneling into existence might be analogous to this wave function collapse on a cosmic scale. The universe transitioned from a superposition of possibilities to a concrete reality with specific initial conditions, those incredibly low entropy conditions, which then allowed the thermodynamic arrow of time to emerge and persist. It's not just that the tunneling happened at a certain moment. The very process of tunneling, with its inherent quantum uncertainty and irreversibility, might be the source from which time's directionality sprang. The precise mechanism by which quantum tunneling instills the arrow of time is still a subject of active research and debate among physicists. Some theories propose specific models where the initial tunneling event breaks certain symmetries in the fundamental laws, while others focus on how the low entropy state required for tunneling naturally leads to the thermodynamic arrow. The philosophical implications are profound. If time's directionality originated at this quantum moment, does that mean time itself wasn't a fundamental property existing before the tunneling? Could time have emerged alongside space and the other fundamental forces of nature in this single, monumental quantum event? This line of thinking suggests that our perception of time as a linear, irreversible flow is not an intrinsic feature of all possible realities, but rather a characteristic of our particular universe, a consequence of its specific origin through quantum tunneling and the resulting low entropy state. It compels us to consider that the arrow of time is perhaps more than just a thermodynamic phenomenon. It could be a fundamental arrow etched into the fabric of reality by the very event that brought the universe into being. One of the most perplexing puzzles in cosmology is the fine-tuning problem. It refers to the astonishing fact that the fundamental physical constants and initial conditions of the universe seem perfectly calibrated for the existence of stars, galaxies, and life as we know it. If these constants were even slightly different, say, the strength of gravity or the mass of an electron, the universe would be a vastly different place, potentially without any complex structures or even stable atoms. The question is, why are these parameters set to such a seemingly improbable degree? Is it just an incredible cosmic coincidence? Some theories involving the universe's initial quantum tunneling event offer a potential explanation, often linking it to the idea of a multiverse. Imagine a vast landscape of possible universes, each with different physical laws and constants. If our universe arose through a quantum tunneling event, it's plausible that this event didn't just produce any universe, but one specific type or perhaps a subset of types from this cosmic landscape. In theories where the universe tunnels into existence from a parent universe or from a state that allows for multiple outcomes, each tunneling event could, in principle, give rise to a universe with a unique set of physical parameters. Think of it like a cosmic lottery, where each quantum tunneling event is a ticket that could result in a universe with different properties. If there are an enormous number of these tunneling events happening in a vast multiverse, then a massive array of potential universes would be generated over potentially infinite time. Some might be short-lived and sterile, ending in a big crunch or expanding too quickly for anything to form. Others might have constants that don't allow for stable atoms or prevent stars from igniting. But within this immense collection, there would inevitably be some universes with parameters just right for complexity, for the formation of galaxies, stars, planets, and eventually life. This is where the controversial yet compelling anthropic principle comes into play. The anthropic principle, in its simplest form, suggests that the reason we observe the universe to have the specific properties it does is because those properties are necessary for observers like us to exist. It's not necessarily saying the universe was designed for us, but rather that we can only find ourselves in a universe where conditions are suitable for life. In the context of quantum tunneling into a multiverse, the anthropic principle provides a selection effect. Out of the countless universes potentially generated by tunneling events with every conceivable combination of parameters, we necessarily inhabit one of the rare universes where the constants are fine-tuned for life. We couldn't exist in a universe where gravity was too strong or the nuclear forces were too weak, so we wouldn't be there to observe those universes. Therefore, our presence acts as a filter, making it unsurprising that we find ourselves in a universe with these seemingly improbable parameters. While this explanation offers a neat solution to the fine-tuning problem by linking it to the sheer number of possibilities in a multiverse born from quantum tunneling, the anthropic principle itself is viewed by some scientists with skepticism. Critics argue that it isn't a true scientific explanation because it doesn't make testable predictions about the fine-tuned values themselves. It simply explains why we observe them. It can feel like a tautology, stating that we see what we see because if we didn't, we wouldn't be here to see it. However, proponents argue that when combined with a physical mechanism like quantum tunneling that produces a vast ensemble of universes with varying parameters, the anthropic principle becomes a powerful tool for understanding why our specific universe appears so special. It shifts the focus from why the universe is fine-tuned to why we observe a fine-tuned universe within a larger reality where most universes might be hostile to life. The specific details of how the tunneling event itself influences the resulting parameters are still theoretical, often linked to the dynamics of the quantum fields involved in the process, but the overarching idea is that the probabilistic nature of quantum tunneling across a landscape of possibilities naturally leads to the emergence of universes with diverse properties, and we simply find ourselves in one of the hospitable ones. It's a theory that uses the mind-bending nature of quantum tunneling and the vastness of the multiverse to address one of the most profound questions about our place in the cosmos. Another profound puzzle the universe presents is the mystery of matter-antimatter asymmetry. When you create particles and antiparticles in high-energy experiments, they're always produced in pairs. According to our standard models, the Big Bang should have created almost exactly equal amounts of matter and antimatter. But look around, everything we see, from the smallest atom to the largest galaxy, is made overwhelmingly of matter. If there had been equal amounts, they would have annihilated each other shortly after the Big Bang, leaving behind a universe filled only with energy, not stars, planets, or us. So, where did all the antimatter go, and why is there this tiny but crucial excess of matter? It's one of the fundamental questions in cosmology, and some theories suggest the universe's very first quantum tunneling event might hold the key. The conditions or processes that occurred during or immediately after this tunneling into existence could have established the initial imbalance between matter and antimatter, a process known as baryogenesis. For baryogenesis to occur, three conditions known as the Sakharov conditions must be met. you need processes that violate baryon number conservation, meaning the total number of baryons like protons and neutrons isn't conserved. You need a violation of charge parity or CP symmetry, which essentially means the laws of physics behave differently for particles and antiparticles. And finally, these processes must happen out of thermal equilibrium. The standard Big Bang model struggles to find a consistent mechanism that meets all three conditions simultaneously in the right amount to explain the observed asymmetry. This is where the unique conditions of a quantum tunneling origin could be significant. The extreme energies and non-equilibrium processes inherent in a cosmic tunneling event might naturally provide the environment necessary for these conditions to be met. Specific mechanisms within tunneling models have been proposed to explain this asymmetry. One idea involves the behavior of hypothetical scalar fields, like the inflaton field we mentioned earlier during the tunneling process. The way these fields transition during the tunneling event could preferentially create slightly more matter particles than antiparticles. Imagine the tunneling event as a dramatic shift in the energy landscape of the universe. As the universe settled into its new vacuum state after tunneling, the dynamics of the relevant quantum fields could have led to reactions that favored the production of matter over antimatter, violating that crucial CP symmetry. The non-equilibrium nature of the tunneling process itself, a rapid and drastic change in the state of the universe, would naturally satisfy the third Sakharov condition. It's a scenario where the very act of the universe coming into being through quantum tunneling imprints a fundamental asymmetry onto its composition. Another proposed mechanism links the matter-antimatter asymmetry to phase transitions that might have occurred immediately after tunneling. As the early universe cooled from its incredibly high initial temperature, it would have undergone phase transitions similar to water freezing into ice. If the tunneling event set up specific initial conditions or triggered particular field dynamics, these subsequent phase transitions could have provided the out-of-equilibrium environment and CP violation needed for baryogenesis. The theory suggests that the tunneling wasn't just a switch from nothing to something, but a complex process that left its signature on the nascent universe, setting the stage for the slight excess of matter that ultimately allowed for everything we see. While these mechanisms are highly theoretical and depend on the specific details of the tunneling model being considered, they offer a compelling possibility that the fundamental imbalance between matter and antimatter, the very reason we exist, is a direct consequence of the universe's bizarre quantum birth. One of the biggest mysteries in modern cosmology is the accelerating expansion of the universe. Instead of slowing down due to the gravitational pull of all its matter, the universe is actually speeding up. The force driving this acceleration is something we call dark energy, and it makes up about 70% of the total energy density of the universe. But despite its dominance, the nature of dark energy remains elusive. We know it's there because of its gravitational effects on cosmic structures and the expansion rate, but we don't know what it is. Some fascinating theories propose that the universe's first quantum tunneling event is intimately connected to the origin and nature of this mysterious force. The idea here is that the energy released during that monumental transition, or maybe subsequent phase transitions triggered by it, could be the source of dark energy. Imagine the universe tunneling from a high-energy false vacuum to a lower-energy true vacuum. The energy difference between these two states has to go somewhere, and it's theorized that this released energy could manifest as the vacuum energy that drives the current acceleration. Different tunneling models might predict distinct properties for dark energy. For instance, if the tunneling event directly transitioned the universe into its current vacuum state, the resulting dark energy might be a constant value throughout cosmic history, often referred to as a cosmological constant. This is the simplest and currently most favored explanation for dark energy, fitting well with observational data. However, if the tunneling event initiated a complex series of subsequent phase transitions, or if the field responsible for tunneling didn't settle immediately into its absolute lowest energy state, dark energy might not be a constant. It could be a dynamic entity that changes over time, a concept known as quintessence. Models where tunneling leads to quintessence might predict a dark energy density that varies with the expansion of the universe, potentially having observable consequences for the growth of large-scale structure or the history of cosmic acceleration. The challenge lies in unifying our understanding of the universe's genesis, that initial quantum tunneling event, with the late-time cosmic acceleration driven by dark energy. How can an event that happened nearly 14 billion years ago still be influencing the universe's expansion today? Theories linking tunneling to dark energy attempt to draw a direct connection. The very vacuum state that the universe settled into after tunneling is the source of dark energy. The energy density of this vacuum state, a fundamental property of the quantum fields that fill space-time, exerts a negative pressure, causing the universe to expand at an accelerating rate. The tunneling event essentially selected or created this specific vacuum state with its associated dark energy density. This means the value of dark energy we observe today isn't a random number, but is determined by the nature of the pre-tunneling state and the dynamics of the tunneling process itself. Another proposed link involves the possibility that the field responsible for the initial tunneling, like the inflaton field, might also be related to the field responsible for dark energy. Perhaps they are different manifestations of the same fundamental field, or the tunneling event left residual effects in the vacuum that later emerged as dark energy. The challenges are significant. We need theoretical frameworks that can consistently describe both the incredibly high energy physics of the early universe's tunneling event and the much lower energy physics governing dark energy's influence today. Observational cosmology is constantly refining our measurements of dark energy's properties, such as whether it's truly a constant or if it changes over time. These observations provide crucial data points for theorists to test whether tunneling-based explanations for dark energy are viable. If future observations reveal that dark energy is dynamic, it would lend support to models where the tunneling event initiated a more complex post-tunneling evolution of vacuum energy. Conversely, if it remains consistent with a cosmological constant, it would favor models where the tunneling directly led to the stable true vacuum state we currently inhabit. The quest to understand dark energy, therefore, is deeply intertwined with the mystery of the universe's earliest moments and whether its accelerating expansion is a lingering echo of its quantum mechanical birth. Beyond the initial tunneling event itself, the conditions it created could have been the catalysts for a series of crucial transformations in the very early universe known as phase transitions. You're probably familiar with phase transitions from everyday life, like water changing from liquid to ice or steam. In the context of the early universe, these were not changes in matter, but in the fundamental forces and fields that govern reality. Immediately after the universe quantum tunneled into existence, it was incredibly hot and dense. As it expanded and cooled, the fundamental forces that are currently separate, like electromagnetism, the weak nuclear force, and the strong nuclear force, might have been unified into a single force at incredibly high energies. As the universe cooled further, this unified force would have undergone a series of symmetry breakings, essentially splitting into the distinct forces we observe today. Think of it like a single crystal forming from a liquid as it cools. The symmetry of the uniform liquid is broken as the ordered crystal structure emerges. One of the key early phase transitions is the electroweak phase transition. At extremely high temperatures, the electromagnetic force and the weak nuclear force were theorized to be unified as the electroweak force. As the universe cooled to around a quadrillion degrees Celsius, an unfathomable temperature, but much cooler than the instant after tunneling, this symmetry broke, causing the electromagnetic force and the weak force to become distinct. This phase transition is also thought to be connected to how fundamental particles acquire mass through their interaction with the Higgs field. The tunneling event likely established the initial temperature and energy density that set the stage for this and other subsequent phase transitions to occur as the universe cooled through critical points. The specific energy scale and timing of the tunneling could directly influence when and how these phase transitions unfolded, impacting the properties of particles and the way forces interact. Another fascinating possibility linked to early phase transitions is the formation of topological defects. If the symmetry breaking during one of these transitions didn't happen perfectly uniformly across the entire universe, it could have left behind remnants in the fabric of spacetime itself. These are like imperfections or wrinkles left over from the cosmic phase change. Examples include cosmic strings, which are incredibly thin but immensely dense lines of energy stretching potentially across the universe, or domain walls, two-dimensional boundaries separating regions of spacetime with different vacuum states. Magnetic monopoles, hypothetical isolated magnetic charges unlike the north and south poles we always find together, are also predicted by some unification theories to be produced during early phase transitions. While none of these topological defects have been definitively observed yet, they are significant because if they exist, they would have been generated at specific energy scales during particular phase transitions, which in turn could be linked back to the initial conditions set by the quantum tunneling event. For instance, the energy scale at which cosmic strings might form is related to the energy of the phase transition that created them. If the tunneling event determined this energy scale, then the observed properties or even the absence of these defects could provide indirect clues about the tunneling process. The search for signatures of these early phase transitions and any resulting topological defects is an active area of research in cosmology. Scientists look for their potential gravitational effects on the cosmic microwave background radiation or on the distribution of galaxies. The idea is that the energy and chaos of the universe's first quantum tunneling were not just a single event but a trigger, initiating a cascade of subsequent transformations that ultimately sculpted the structure of the cosmos we see today, leaving behind potential echoes in the form of these cosmic imperfections. Stepping into the realm of string theory, we encounter another fascinating perspective on how the universe might have begun with a quantum tunneling event. String theory is one of the leading candidates for a theory of everything, aiming to unify all fundamental forces and particles. It proposes that the most basic constituents of the universe aren't point-like particles, but rather tiny, vibrating strings of energy. The way these strings vibrate determines the type of particle they represent, much like different notes can be played on a violin string. But string theory isn't limited to just strings. It also predicts the existence of higher dimensional objects called branes, short for membranes. These branes can be two-dimensional surfaces, three-dimensional volumes, or even exist in more dimensions, potentially up to 9 or 10 spatial dimensions plus time posited by string theory. Our familiar four-dimensional spacetime could simply be a brane within this higher dimensional landscape. In the context of string cosmology, which applies string theory to the origin and evolution of the universe, the idea is that the universe's birth could be intricately linked to the behavior and interactions of these branes. One compelling scenario is that our universe, our four-dimensional brane, came into existence through a quantum tunneling event from a higher dimensional space, perhaps involving the collision or close approach of other branes. Imagine multiple branes existing in a higher dimensional bulk space. If these branes are moving towards each other, they might classically be prevented from colliding by some energy barrier or configuration. However, through quantum tunneling, these branes could pass through this barrier, interact, and in the process, create the energy and conditions necessary for our universe, our own brane, to emerge and begin its expansion. This is sometimes referred to as a brane collision or ekpyrotic/cyclic scenario in string cosmology, where the tunneling happens between branes. different string theory models offer varying descriptions of the pre-tunneling state and the dynamics of the tunneling event. In some models, the tunneling might involve a transition from a state where branes are separated to a state where they are in contact, triggering the release of energy that forms our universe. In others, it might be a tunneling process that changes the configuration or topology of the branes themselves. For example, a brane might tunnel from one stable configuration to another, and this transition could be the cosmic birthing event. The dynamics of these tunneling events are described by the complex mathematics of string theory, involving how the branes move and interact within the higher dimensions, governed by the tension of the strings and the geometry of the extra dimensions. The specific type of string theory model, there are several compatible versions, can influence the details of how this tunneling process might work and what kind of universe would result. One of the significant challenges with connecting theoretical string cosmology, including brane tunneling scenarios, to observable phenomena is the incredible energy scale at which string theory operates, the Planck scale, far beyond the reach of our current particle accelerators. The predictions of string theory are often expressed in terms of these extra dimensions and branes, which are not directly observable in our everyday four-dimensional world. Making contact with cosmology requires finding ways for these fundamental stringy and brane-like features to leave subtle imprints on the universe we see today, perhaps in the patterns of the cosmic microwave background radiation, the distribution of galaxies, or even gravitational waves. Scientists are actively researching potential observational signatures that could distinguish between different string cosmology models and potentially provide evidence that our universe's origin involved brane dynamics and quantum tunneling in a higher dimensional reality. While still highly speculative, the idea that our entire universe is a consequence of a quantum tunneling event involving these fundamental stringy objects within a higher dimensional space is a truly mind-bending possibility at the forefront of theoretical physics. Consider the mind-bending holographic principle, an idea that suggests the universe we experience in three spatial dimensions could somehow be a projection or encoding of information stored on a two-dimensional surface, like a cosmic hologram. It sounds like science fiction, but it's a serious concept arising from research into black holes and quantum gravity. The most famous example is the anti-de Sitter/conformal field theory correspondence, or AD-S/CFT correspondence, which relates a theory of gravity in a certain type of spacetime to a quantum field theory without gravity living on its boundary. It's like having a detailed instruction manual for building a complex three-dimensional object written entirely on a flat piece of paper. Now, how might the universe's first quantum tunneling event relate to this deeply strange holographic idea? Some theories propose that the initial conditions of our universe, those precise parameters and configurations established during or immediately after its tunneling into existence, could be fundamentally linked to this holographic encoding. The argument goes that if the universe has a holographic nature, then the information that defines its state at any given time, including its initial state, might be encoded on some boundary. In the context of the early universe and tunneling, this boundary might not be a physical boundary in the traditional sense, but perhaps a conceptual one related to the degrees of freedom available at the moment of creation. Imagine the pre-tunneling state or the tunneling process itself as a transition where the information about the future universe was somehow being written onto this lower dimensional surface. The act of quantum tunneling, a non-classical jump from one state to another, could be the very mechanism by which this holographic encoding was established, determining the initial conditions and subsequent evolution of the three-dimensional reality we inhabit. It's as if the universe's blueprint was drawn on a cosmic canvas during the tunneling, and our three-dimensional reality is the resulting projection. This perspective offers a different way to think about the challenging problem of quantum gravity in the early universe. Singularities, like the one predicted by general relativity at the Big Bang, are points where our current understanding breaks down. Quantum gravity theories, including those involving tunneling, aim to resolve these singularities and provide a consistent description of the universe at its most extreme moments. The holographic principle offers a potential tool for this. By relating a theory of gravity in higher dimensions to a simpler quantum field theory in lower dimensions, it might provide a way to study the quantum gravity aspects of the early universe using the more tractable tools of quantum field theory on the boundary. The idea is that the complex, high-energy processes of the tunneling event and the immediate aftermath might be describable in terms of a holographic theory on a lower dimensional space, giving us a different window into understanding those otherwise inaccessible conditions. For instance, if the universe tunneled into existence from a state described by a certain type of quantum field theory on a boundary, studying that theory could provide insights into what kind of three-dimensional universe would emerge and what its initial properties would be. The mathematics of these boundary theories might be more manageable than trying to directly model quantum gravity in the bulk spacetime of the tunneling universe. The holographic principle provides a potential duality, a way of looking at the same physics from two different perspectives, one of which might be more amenable to calculation and understanding, particularly in the extreme conditions of the universe's birth. It suggests that the information content and the fundamental nature of the universe might be more constrained and describable than previously thought, potentially encoded in a holographic manner, and that the tunneling event was the process by which this encoding translated into our expanding three-dimensional reality. While still a highly theoretical area, the connection between quantum tunneling and the holographic principle offers a deeply fascinating, albeit challenging, avenue for exploring the fundamental nature of reality and how it all began. Let's consider a concept that might seem utterly alien: non-commutative spacetime. We're used to thinking of space and time as smooth and well-behaved. If you move 3 feet east and then 2 feet north, you end up in the same place as if you moved 2 feet north and then 3 feet east. The order doesn't matter. This is because in our everyday experience, the coordinates of space and time commute. The order in which you combine movements or measure properties doesn't affect the final outcome. However, at the extreme conditions of the very early universe, particularly at those near Planck scale sizes and energies, some theories suggest this might not be the case. They propose that at this fundamental level, spacetime might be non-commutative, meaning the order of operations does matter. Measuring one property of spacetime might affect your ability to precisely measure another. Much like in quantum mechanics, measuring a particle's position affects your knowledge of its momentum. This non-commutative geometry is a radical departure from our standard understanding of differential geometry used to describe spacetime in general relativity. It suggests that spacetime at its most fundamental level is not a smooth manifold, but has a more intricate, almost granular or fuzzy structure where points can't be precisely pinpointed simultaneously in all dimensions. The theoretical motivations for considering non-commutative spacetime in early universe cosmology are compelling. One major driver is the attempt to unify general relativity and quantum mechanics. At the Planck scale, both gravity and quantum effects are significant, and our standard theories clash. Non-commutative geometry offers a mathematical framework that might be able to bridge this gap, providing a description of spacetime where the uncertainties of quantum mechanics are intrinsically woven into the geometric structure itself. Furthermore, incorporating non-commutativity might help resolve issues like the singularities predicted by general relativity, such as the Big Bang singularity. If spacetime is fundamentally non-commutative at these extreme scales, the concept of a single point of infinite density might not even be well defined. Now bring quantum tunneling into this picture. Theories linking tunneling with non-commutative spacetime propose that the universe began in a state where spacetime was fundamentally non-commutative. This pre-tunneling state wasn't the smooth, commutative spacetime we experience today. Instead, it was a turbulent quantum realm described by non-commutative geometry. The universe then quantum tunneled from this non-commutative state into the commutative spacetime we observe. Think of it as a phase transition, but instead of changing from liquid to solid, the fundamental nature of spacetime geometry changed. This tunneling event could have been triggered by some instability in the non-commutative vacuum or by fluctuations at the quantum level in this unusual geometric landscape. The tunneling event in this context isn't just about appearing from nothing or expanding rapidly. It's about a fundamental transformation in the very structure of reality, from a non-commutative quantum geometry to the smooth commutative spacetime of our universe. The energy released or the dynamics of the fields involved during this tunneling could have been what smoothed out the non-commutative fuzziness, allowing the familiar rules of geometry to emerge on larger scales. Different models within this framework specify the mathematical details of the non-commutative geometry and the tunneling process. They explore how the parameters of the non-commutative state would influence the properties of the resulting commutative universe, potentially leaving subtle, though currently unobservable, signatures on the cosmos. It's a highly theoretical area, pushing the boundaries of both mathematics and physics, but it offers a glimpse into a possible reality where the very concept of space and time was radically different before the universe took its first breath through a quantum tunneling event, transitioning from a realm where order mattered in a way we can barely comprehend to the familiar regularities. Space-time we call home. Let's venture into one of the most mind-bending and controversial ideas: the possibility that our universe didn't tunnel into existence from nothing or a previous state, but actually emerged from the heart of a black hole or a similar type of singularity. We're used to thinking of black holes as cosmic drains, regions where gravity is so intense that nothing, not even light, can escape once it crosses the event horizon. But what happens inside a black hole, at the singularity where matter is crushed to infinite density and spacetime, is thought to break down. This is a realm of extreme physics where our current understanding falters, and it's precisely these extreme conditions that some theories link to the birth of a new universe. One concept associated with this idea is the hypothetical white hole. A white hole is often described as the time-reversed version of a black hole. While nothing can escape a black hole, a white hole is a region from which matter and energy could only emerge and nothing could ever enter. It acts as a cosmic fountain rather than a drain. Though never observed and highly theoretical, some cosmological models have explored the idea that the singularity at the center of a black hole might, through quantum effects, somehow connect to a white hole, which then serves as the origin point for a new universe. The idea unfolds like this: as matter collapses into a black hole, it approaches the singularity. According to classical general relativity, this is the end of the line, a point of infinite density from which nothing can escape and where time effectively ends. However, quantum mechanics suggests that infinities might be smoothed out at the Planck scale. The extreme quantum fluctuations and incredibly high energy densities near a black hole singularity could trigger a quantum tunneling event. Instead of just remaining a singularity, the compressed matter and energy could quantum tunnel through this classically impenetrable barrier, the singularity itself, and emerge as a new, expanding region of space-time, a baby universe potentially appearing as a white hole from the perspective of an outside observer. Imagine the singularity as a barrier in the fabric of space-time. Classically, you're trapped there, but quantum tunneling allows a possibility, however small, of passing through that barrier into a different configuration of space-time, a new universe. This black hole cosmology, sometimes called a fecund universe model, suggests a cyclical process where universes spawn new universes inside their black holes. Our universe could have been born from a black hole in a parent universe, and in turn, the black holes within our own universe might be giving birth to other universes. This elegantly sidesteps the need for an absolute beginning from nothing, instead proposing a continuous, perhaps infinite, process of cosmic reproduction through quantum tunneling at singularities. The properties of the black hole from which our universe tunneled its mass, rotation, etc., might even influence the initial conditions or fundamental constants of our own universe. However, this theory faces significant challenges and controversies. One major hurdle is the information paradox. When matter falls into a black hole, the information about its quantum state seems to be lost at the singularity, violating a fundamental principle of quantum mechanics that information should always be conserved. If a new universe is born from that singularity, where does the information from the collapsed matter go? Does it somehow tunnel into the new universe, or is it truly destroyed? This remains a major unresolved problem in theoretical physics, and any black hole tunneling cosmology must grapple with it. Another challenge is explaining why the universe that tunnels out is so vastly different from the black hole it emerged from, expanding and relatively smooth, unlike the extreme curvature and density within the event horizon. Furthermore, white holes are not predicted by standard general relativity in a stable way. They are often seen as mathematically possible but physically unlikely under typical conditions. Despite these difficulties, the idea that the universe's dramatic birth was a quantum tunneling event from within the ultimate cosmic drain, a black hole singularity, remains a captivating and actively researched, albeit highly speculative, area of theoretical cosmology. Consider a radical notion that flips our understanding of reality on its head. The idea that space-time, the very fabric of the universe we inhabit, isn't a fundamental entity but something that emerges from a deeper, more fundamental quantum reality. We're used to thinking of space as the stage on which everything happens and time as the progression through which events unfold. But what if these aren't the ultimate building blocks? What if they are, in fact, emergent properties arising from something more basic, something that existed before space-time as we know it? This is the core of theories of emergent space-time, and it ties intriguingly into the concept of the universe's first quantum tunneling event being the very process of this emergence. Imagine a state before the universe, not just empty space, but a state where space and time simply didn't exist in the way we understand them. Perhaps it was a network of relationships, a collection of quantum bits of information, or some other structure we can barely conceive. The universe's first quantum tunneling event, in this context, wasn't just a jump from a false vacuum or a black hole singularity. It was the spontaneous emergence of spacetime itself from this pre-geometric, pre-temporal quantum realm. How might spacetime emerge from a state without it? Different theoretical approaches offer possibilities. One fascinating idea links the emergence of spacetime to quantum entanglement. Entanglement is that strange quantum connection where two particles can be linked in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. Some theories, like those inspired by the AD/CFT correspondence we touched on earlier, suggest that the geometry of spacetime in the bulk could be directly related to the degree of entanglement between quantum degrees of freedom residing on a boundary or in a more fundamental theory. In this view, space, and perhaps time, could be seen as built from the correlations and entanglements between these fundamental quantum constituents. If the pre-tunneling state was one of profound quantum correlation or a particular configuration of entangled degrees of freedom, the quantum tunneling event could have been the catalyst that, through a sudden change or restructuring of these correlations, gave rise to the connected, extended spacetime we observe. The tunneling would be the phase transition from a state of pure quantum correlation to a state where these correlations manifest as the geometric properties of spacetime. Another approach to emergent spacetime is causal set theory. This theory posits that at the most fundamental level, spacetime is not continuous but is made up of discrete, indivisible points like tiny atoms of spacetime. These points are ordered by a relation that describes causation, meaning that some points are before or after others, establishing a fundamental arrow of time from the outset. The overall structure formed by these causally related points is what approximates continuous spacetime on larger scales, much like a collection of dots can form a continuous image when viewed from a distance. In a causal set framework, the universe's birth might be viewed as the initial growth or emergence of this causal set from a state where no such causal structure existed. The quantum tunneling event could be the first instantiating of this causal order, the first appearance of these spacetime atoms and their causal relationships from a void that had neither events nor the relations between them. It's an emergence of order and structure from a state of fundamental formlessness or non-existence in a causal sense. The tunneling event would be the non-classical leap that created the initial elements of this causal set and set the process of its growth in motion, leading to the vast and complex spacetime we inhabit. The implications of spacetime being emergent are deep and far-reaching. It suggests that gravity, which in general relativity is described as the curvature of spacetime, is also not fundamental but is a consequence of this emergent structure. Finding a quantum theory of gravity becomes a quest to understand the more fundamental quantum reality from which spacetime emerges and how gravity arises from its properties. If the universe's initial tunneling was the process of spacetime's emergence, it means the conditions and dynamics of that tunneling event would have fundamentally shaped the nature of spacetime itself, its dimensionality, its curvature, and perhaps even its fundamental constants. The search for a theory of quantum gravity is inextricably linked to understanding this potential emergence and the role of quantum tunneling in that process. It's a journey into the pre-spacetime abyss, seeking to understand how our familiar reality sprang into being from a realm utterly devoid of the dimensions and temporal flow that define our existence. It compels us to consider that spacetime is less like an unchangeable stage and more like a dynamic, emergent phenomenon, born from a monumental quantum leap. Beyond simply creating the universe, some theories propose that the universe's first quantum tunneling event left behind profound and potentially observable scars in the very fabric of spacetime cosmic strings or other topological defects. Imagine the early universe as an incredibly high-energy field, uniform and smooth, much like a liquid before it freezes. As the universe expanded and cooled after the initial tunneling, it underwent rapid phase transitions, similar to that change from liquid to solid. If these transitions weren't perfectly synchronized across the entire cosmos, they could have left behind imperfections like cracks or wrinkles in the newly solidified structure of spacetime. These imperfections are what physicists call topological defects, and they can take several forms depending on the nature of the phase transition that created them. Cosmic strings are one type, incredibly thin, one-dimensional lines of concentrated energy that could stretch across vast distances. They aren't made of matter in the usual sense, but are rather persistent features in the field that underwent the phase transition. Other defects include domain walls, which are two-dimensional boundaries separating regions where the field settled into different but equally valid states, and magnetic monopoles, hypothetical point-like objects carrying an isolated magnetic charge, unlike the north and south poles that always come in pairs in everyday magnets. The crucial link to the universe's initial quantum tunneling event lies in the idea that the tunneling process itself could have determined the specific conditions and parameters of these early phase transitions. The energy scale at which the tunneling occurred or the particular vacuum state the universe tunneled into would directly influence the temperature and energy density of the nascent cosmos as it began to cool. These initial conditions are critical for determining whether and what type of phase transitions would happen and at what cosmic time they would occur. For instance, if the tunneling happened at a very high energy scale and led to a rapid drop in energy density, it might have triggered a specific type of phase transition that favors the formation of cosmic strings. Conversely, tunneling into a different vacuum state or with different energy dynamics might lead to conditions more conducive to the formation of domain walls or monopoles. The tunneling event, in this view, wasn't just about the universe appearing. It was about setting the precise stage for the subsequent cosmic evolution, including the potential formation of these spacetime defects. While cosmic strings and other topological defects remain theoretical, they are actively searched for because if they exist, they would leave distinct observational signatures on the universe we see today. Cosmic strings, being incredibly dense lines of energy, would bend spacetime around them, causing gravitational lensing effects where light from distant objects is distorted or even appears as multiple images. Astronomers look for these characteristic gravitational lensing patterns as potential evidence for cosmic strings. Another key area of search is the cosmic microwave background radiation, the faint afterglow of the Big Bang. Cosmic strings passing through the early universe would create ripples or characteristic patterns in this radiation due to their gravitational influence. Specific temperature anisotropies or polarization patterns in the CMB could potentially be interpreted as the imprint of cosmic strings or other defects formed shortly after the universe tunneled into existence. The potential detection or definitive non-detection of these topological defects has significant implications for theories of the early universe and the nature of the initial tunneling event. If, for example, cosmic strings with predicted properties related to a specific tunneling model were found, it would lend strong support to that model. On the other hand, if sensitive observations rule out the existence of these defects with properties predicted by certain theories, those theories linking the tunneling to their formation would need to be revised or discarded. The search for these relics of the early universe, these potential imperfections left behind by cosmic phase transitions triggered by the universe's initial quantum tunneling, is therefore a vital part of probing the mysteries of our origins, using the vastness of the cosmos as a laboratory to test the most fundamental theories about reality's birth. One of the most powerful tools we have for probing the very early universe is the cosmic microwave background, or CMB. Think of it as a baby picture of the universe, a faint glow of microwave radiation that permeates all of space, left over from about 380,000 years after the Big Bang. Before this time, the universe was a hot, dense plasma where light couldn't travel freely. As it cooled, electrons and protons combined to form neutral atoms, and the universe became transparent, allowing photons to stream out. These photons have been traveling ever since, stretched and cooled by the universe's expansion to become the microwaves we detect today. But the CMB isn't perfectly uniform. It contains tiny temperature fluctuations, variations on the order of parts per 100,000. These subtle differences in temperature represent regions of slightly higher or lower density in the early universe. Over billions of years, gravity amplified these initial density perturbations, pulling matter together to form the first stars, galaxies, and the vast cosmic structures we see today. So, the patterns locked within the CMB are essentially the seeds of cosmic structure, a direct snapshot of the universe's initial conditions on large scales. This is where the universe's first quantum tunneling event enters the picture in a truly profound way. Some theories propose that those crucial initial density fluctuations, the ones that eventually grew into everything we see, weren't just random occurrences after the Big Bang. Instead, they were generated during or immediately after the universe's quantum tunneling into existence. The idea is that the tunneling process wasn't perfectly smooth and uniform across space. As the universe transitioned from its pre-tunneling state to the state we inhabit, there would have been quantum fluctuations in the fields responsible for the tunneling and the subsequent rapid expansion. These fluctuations, amplified by the incredibly fast expansion that followed, would have been imprinted onto the fabric of space-time and distributed throughout the nascent universe as tiny variations in energy density. Imagine the tunneling as a sudden event, and the fields involved weren't perfectly calm. they were subject to the inherent jitteriness of the quantum world. This quantum jitter, magnified to cosmic scales by the subsequent expansion, left its mark as those tiny temperature differences in the CMB. Different theories about the nature of the initial quantum tunneling would predict slightly different characteristics for these imprinted fluctuations in the CMB. For example, theories involving specific types of potential energy landscapes for the quantum field that drove the tunneling might predict a particular spectrum of fluctuations, how the strength of the fluctuations varies with their size on the sky. Some tunneling models might favor slightly larger fluctuations on certain scales compared to others, or predict specific statistical properties for the patterns in the CMB. The degree to which the fluctuations are random or exhibit non-Gaussian features patterns that deviate from a simple random distribution can also vary depending on the details of the tunneling scenario. The properties of any topological defects potentially created during subsequent phase transitions, as discussed earlier, would also leave their own distinct imprints on the CMB which can be searched for. The challenge for theorists is to develop specific tunneling models that make testable predictions about the statistical properties and patterns of the CMB fluctuations. This is why the CMB is such a vital window into the universe's earliest moments. Satellites like the Planck satellite have mapped the CMB with incredible precision, providing cosmologists with a treasure trove of data about those initial fluctuations. By comparing the observed patterns and statistics of the CMB fluctuations to the predictions of different theoretical models, including those involving various types of quantum tunneling origins, scientists can test and constrain these theories. If a particular tunneling model predicts a specific pattern in the CMB that is then observed, it provides strong support for that model. Conversely, if the observed CMB data contradicts the predictions of a model, that model can be ruled out or significantly modified. The search for the origins of the cosmos has, in a very real sense, become a meticulous analysis of this ancient light, seeking to decode the subtle patterns imprinted billions of years ago by the universe's first moments, potentially revealing the signature of its quantum tunneling birth and the turbulent quantum realm from which cosmic structure sprang. Exploring the universe's first quantum tunneling event also brings us face to face with a grand ambition in theoretical physics, the search for grand unified theories, or GUT. Imagine a time in the universe's history at incredibly high energies where the fundamental forces we experience today, the electromagnetic force, the weak nuclear force responsible for radioactive decay, and the strong nuclear force that binds atomic nuclei together, weren't distinct but were instead unified into a single master force. This is the core idea behind GUTs. These theories propose that as the universe cooled from its fiery birth, this unified force underwent symmetry-breaking phase transitions, splitting into the separate forces we see today, much like water freezing causes a change in its fundamental state. The energy scale at which this unification and subsequent splitting is expected to happen is incredibly high, far beyond the reach of even our most powerful particle accelerators, like the Large Hadron Collider. We're talking about energies approaching the Planck scale, precisely the kind of energies thought to be involved in the universe's very first moments. The potential connection between the initial quantum tunneling and GUTs is compelling because the energy scales line up. If the universe quantum tunneled into existence from a state of extremely high energy density, this energy scale could be directly related to the unification scale predicted by GUTs. The pre-tunneling state itself might be described by a theory where the forces are unified. The act of tunneling could be the transition from this unified state to a state where the symmetries are broken and the forces begin to differentiate. Think of the tunneling as the event that pushed the universe off a high-energy plateau where the forces were unified, down into a valley where they became distinct. The characteristics of the tunneling, the energy difference between the initial and final states, the dynamics of the fields involved could therefore be intimately linked to the specific nature of the unified force and how it breaks down. Different JUT models predict different energy scales for unification and different ways in which the symmetry breaking occurs. If the universe's birth was a quantum tunneling event, its details might provide clues about which of these theoretical JUT models is the correct description of nature at its most fundamental level. Furthermore, the initial configuration of the universe immediately after tunneling would reflect the state of the fundamental fields at that incredibly high energy. The way these fields settled into what we call the vacuum state of our universe after tunneling would be dictated by the rules of the unified force at that scale. The properties of the particles and forces that emerged as the universe cooled would, therefore, carry the imprint of the JUT from which they sprang. For example, some JUTs predict the existence of very massive particles called X and Y bosons, which mediate interactions between quarks and leptons and could facilitate proton decay, a hypothetical process where protons break down into lighter particles. If proton decay were observed, its rate would provide a crucial piece of evidence for or against specific JUT models, and by extension, could offer insights into the energy scale and nature of the phase transition that occurred after the universe's quantum tunneling birth. The search for evidence of JUTs and their potential connection to the universe's origin is a major focus of experimental physics, even if the direct energy scale is out of reach. Experiments searching for proton decay, though so far unsuccessful, continue to set limits on the lifetime of the proton, which constrains different JUT models. Other experiments look for rare processes predicted by JUTs, such as neutrino oscillations, which have provided compelling evidence that neutrinos have mass, a result that is difficult to explain without physics beyond the standard model, potentially within a JUT framework. The hope is that by probing physics at the highest accessible energies in particle accelerators, or by looking for these rare processes, we can gather indirect evidence for the existence of a JUT and learn more about the energy scale at which unification occurs. If that energy scale aligns with theoretical expectations for the universe's initial quantum tunneling event, it would provide a powerful piece of the cosmic puzzle, suggesting that the birth of our universe was not just a random event, but a predictable outcome of the fundamental unified laws of physics, a transition from a state where reality was governed by a single elegant force to the complex world of distinct forces we experience today. The universe's tunneling origin, therefore, could be a key to unlocking the secrets of the ultimate unified laws that govern everything. One of the most unsettling implications of quantum mechanics is the fuzzy distinction between observer and observed. Unlike in classical physics, where you can measure a system without significantly changing it, at the quantum level, the act of observation itself can influence the outcome. This leads to mind-bending concepts like wave function collapse, where a quantum system exists in a superposition of multiple possible states until it is measured, at which point it collapses into a single definite state. Now apply this idea to the universe as a whole. Some deeply theoretical and often controversial interpretations of quantum mechanics suggest that the universe itself, being a quantum system, might not have had a definite existence or specific properties until some form of observation occurred. In this context, the universe's first quantum tunneling event isn't just a physical transition. It could be fundamentally linked to the emergence of a classical reality from a quantum superposition, potentially involving the role of observers, however rudimentary. This is where things get truly speculative and delve into the philosophical underpinnings of quantum mechanics. One line of thinking explores the idea that the universe, before tunneling, existed in a kind of quantum superposition of all possible initial conditions and states different energy densities, different spacetime geometries, different sets of fundamental constants. It was a realm of pure quantum possibility, a cloud of potential realities. The quantum tunneling event, in this view, wasn't just about physically crossing a barrier. It was the moment this cosmic wave function collapsed, selecting one particular set of initial conditions out of the infinite possibilities. But what triggered this collapse? Some interpretations of quantum mechanics, like the Copenhagen interpretation, suggest that measurement by an observer causes collapse. In the context of the early universe, this raises a profound question. Who or what was the observer that caused the universe's initial state to become definite? Different theories propose possibilities. Some suggest that the universe itself, as it reaches a certain level of complexity, becomes its own observer, or that the interaction between different quantum fields within the nascent universe at the moment of tunneling constitutes a form of self-observation leading to collapse. Another perspective, offered by the many worlds interpretation of quantum mechanics, avoids wave function collapse altogether, suggesting that instead of collapsing, the act of observation or interaction simply causes the universe to split into multiple parallel branches, each representing a different possible outcome. In this view, the quantum tunneling event might not be a collapse into a single reality, but rather the point where the initial quantum superposition of the universe diversified into a multitude of separate universes, each resulting from a different tunneling trajectory or outcome. Our universe would simply be one branch among many, corresponding to a particular tunneling path and a specific set of resulting properties. The connection between the universe's quantum tunneling origin and the observer problem forces us to confront fundamental questions about the nature of reality and measurement. If the universe's initial state was determined by quantum processes involving superposition and potential collapse, does that mean the existence of observers, even future ones, was somehow linked to its very beginning? Some interpretations suggest a form of retrocausality, where events in the future, like the emergence of conscious observers, could somehow influence the outcomes of past quantum events, including the universe's initial tunneling. This is highly speculative and debated, but it highlights the deep philosophical implications of taking quantum mechanics seriously when applied to the cosmos as a whole. While there's no consensus on how the observer problem fully integrates with cosmological tunneling theories, the very notion that the universe's birth required some form of interaction or observation to solidify its state from a quantum superposition is a testament to the mind-bending challenges at the intersection of quantum mechanics and cosmology, suggesting that perhaps reality isn't fully formed until it is, in some sense, perceived or interacted with. Beyond the forces we understand, some theories propose the existence of hidden sectors, realms of particles and fields that interact only very weakly with the matter and forces we know, making them incredibly difficult to detect. These hidden sectors might contain their own set of particles, forces, and symmetries, existing alongside our visible universe but largely decoupled from it. They are often invoked in theoretical physics to explain various mysteries, such as the nature of dark matter or the precise mass of the Higgs boson. Now consider the universe's first quantum tunneling event through the lens of these hidden sectors. One intriguing possibility is that the tunneling process didn't just involve the fields and degrees of freedom of our visible universe, but also those of a hidden sector. The tunneling could have been a transition involving both our sector and a hidden one, or it could have opened up a connection between them, allowing for subtle interactions that shaped the early universe. The simplest scenario is that the pre-tunneling state included a hidden sector, and the tunneling event was a transition that brought both our sector and the hidden one into their current vacuum states. In this case, the initial conditions established by the tunneling would apply to both sectors. The energy released during tunneling would be distributed between them, and the subsequent expansion and cooling would affect the evolution of particles and forces in both realms. The interaction between our visible sector and the hidden sector might be incredibly weak, perhaps mediated by gravity or through very rare interactions involving hypothetical messenger particles that connect the two realms. However, even weak interactions during the extremely high energy and dense conditions immediately after tunneling could have significant consequences. For instance, the properties of particles in the hidden sector could influence the rate of expansion or the distribution of energy in our sector, potentially leaving subtle imprints on the cosmic microwave background or the formation of large-scale structure. A more complex and fascinating possibility is that the quantum tunneling event was not just a transition within pre-existing sectors, but the very event that created or connected our visible sector with a hidden one. Perhaps the pre-tunneling state was primarily the hidden sector, and our visible universe quantum tunneled into existence as a sort of bubble within it. Or maybe the tunneling event involved a transition from a state where the hidden and visible sectors were deeply intertwined and indistinguishable to a state where they separated into distinct, weakly interacting realms. In this scenario, the energy scale and specific dynamics of the tunneling event would determine not just the initial conditions of our visible universe, but also the properties of the hidden sector and the strength of the interactions between them. The tunneling could be the origin story for not just our reality, but for a more complex multi-sector cosmos. The challenge, of course, is finding evidence for these hidden sectors. By their nature, they are designed to be elusive. However, scientists are exploring potential observational signatures. Dark matter is a prime candidate for being a particle residing in a hidden sector, interacting with our matter only through gravity. If dark matter is indeed part of a hidden sector whose properties were determined by the universe's initial tunneling, then understanding dark matter's properties could provide indirect constraints on the tunneling models. Other potential signatures could involve very subtle deviations from predicted distributions of particles in high-energy collisions or unexpected decay modes of known particles, which might be mediated by messenger particles from a hidden sector whose existence was initiated by the cosmic tunneling event. The search for hidden sectors is ongoing in particle physics and cosmology, and if they exist, their properties and our ability to detect them might ultimately provide a link back to the incredibly energetic and mysterious moments of the universe's birth through quantum tunneling, suggesting that our visible reality is just one part of a larger, interconnected cosmic structure. Let's explore a fascinating concept known as quantum entanglement entropy and its potential role in describing the state from which the universe might have quantum tunneled into existence. Quantum entanglement, as we touched on earlier, is that bizarre quantum connection where the fate of two or more particles are linked, no matter how far apart they are. Entanglement entropy is a measure of the degree of this entanglement between different parts of a quantum system. The more entangled two parts are, the higher the entanglement entropy between them. It's a concept particularly relevant in quantum field theory and the search for quantum gravity, as it relates to the information content and correlation within quantum systems. Some theoretical frameworks suggest that entanglement entropy could play a fundamental role in describing the structure of spacetime itself, particularly at the Planck scale. For example, in the context of the holographic principle, the area of a region of spacetime is related to the entanglement entropy of the quantum degrees of freedom on its boundary. Applying this to the universe's origin through quantum tunneling, some theories propose that the pre-tunneling state wasn't empty space or a simple false vacuum, but a state characterized by a very high level of quantum entanglement entropy. Imagine a state where all the fundamental quantum degrees of freedom that would eventually constitute the particles and fields of our universe were maximally entangled with each other, perhaps without any defined spatial separation. It was a state of pure, undifferentiated quantum correlation. The quantum tunneling event, in this view, wasn't just about transitioning across an energy barrier. It was a process that somehow reorganized this entanglement, leading to the emergence of spacetime and the localization of particles. The tunneling could be seen as a sudden decrease or restructuring of the total entanglement entropy, a transition from a state of maximal, formless correlation to a state where entanglement exists between spatially separated regions, giving rise to the geometric properties of spacetime we observe. The idea is that the initial tunneling process would take the universe from a state where entanglement was global and uniform to a state where entanglement is partitioned between different regions, and it's this partitioning and the resulting entanglement structure that defines the emergent spacetime. The geometry and connectivity of spacetime could, in this picture, be a manifestation of how entanglement is distributed after the tunneling event. Different tunneling trajectories or initial conditions might lead to different patterns of entanglement partitioning, and thus different spacetime geometries or perhaps even different numbers of spatial dimensions. The complexity and structure of the universe we see today could be seen as a consequence of the specific way entanglement was disentangled or reorganized during that initial quantum leap. The energy and dynamics of the tunneling process would be intricately linked to the changes in entanglement entropy. As the universe tunnels from a state of high entanglement entropy to a state where entanglement is structured to form spacetime, energy would be released, potentially driving inflation or other early universe processes. The specific value of the vacuum energy, which could be related to dark energy, might even be connected to the residual entanglement entropy of the vacuum state after tunneling. This perspective offers a deeply quantum mechanical view of cosmic origins, suggesting that the universe's birth was a transition from a state defined by pure quantum correlation to a state where that correlation is expressed as the vast, expanding spacetime we inhabit. While measuring entanglement entropy at cosmic scales is currently beyond our capabilities, theoretical developments in quantum gravity and information theory continue to explore these profound connections, suggesting that the universe's first quantum tunneling event was not just a physical happening in space and time, but perhaps the very process by which space and time, as manifestation. Quantum entanglement first came into being from a state of pure quantum correlation. Let's now turn our attention to a truly mind-bending possibility, that the universe's very first quantum tunneling event might not have been destined to produce a universe exactly like ours. Imagine a cosmic lottery where the outcome isn't predetermined and different draws can yield dramatically different results. Some theories suggest that the initial quantum tunneling event could have resulted in a universe with fundamentally different physical laws, different fundamental constants, or even a different number of spatial dimensions than the ones we experience. This idea arises from the landscape of possible vacuum states in quantum field theory and string theory. Picture a complex, multi-dimensional landscape with many valleys and hills. Each valley represents a possible vacuum state, a stable configuration of quantum fields with a specific energy level and a unique set of physical properties, like the masses of particles and the strengths of forces. Our universe is presumably sitting in one of these valleys, our current vacuum state. The idea is that there isn't just one possible vacuum state, but potentially a vast or even infinite number of them, each corresponding to a different set of physical laws. If the universe began by quantum tunneling from a higher energy state, perhaps a different vacuum or a state without spacetime, the destination of that tunneling wasn't necessarily unique. The process of tunneling itself is probabilistic. Just as a particle tunneling through a barrier has a certain probability of appearing on the other side, the universe tunneling into existence might have had a non-zero probability of ending up in any one of these different vacuum states, each corresponding to a universe with its own distinct physics. Imagine the pre-tunneling state as being on a high plateau in this landscape of possibilities. The tunneling event is a descent into one of the valleys, but there are many valleys to choose from, each representing a different potential outcome for the fundamental laws of physics. The specific trajectory of the tunneling event through this landscape could determine which valley the universe landed in, and thus what its physics would be. For example, in some string theory models, the shape and properties of the extra dimensions can vary, and these variations determine the values of fundamental constants and the structure of particle interactions in our four-dimensional spacetime. The landscape of possible vacuum states in string theory often corresponds to different configurations of these extra dimensions. A quantum tunneling event could be a transition from a state with one configuration of extra dimensions to a state with a different configuration, resulting in a universe with a different set of physical laws. One universe might have slightly stronger gravity, another might have a different relationship between electromagnetism and the nuclear forces, or even a different speed of light. Some theoretical models even allow for the possibility that the number of felt spatial dimensions could be different in other vacuum states, perhaps more or fewer than the 3 large spatial dimensions we observe. The implications of this idea for the uniqueness of our universe are profound. If tunneling is a random process across a landscape of possibilities, then our universe, with its specific set of physical laws and constants, might just be one outcome among countless others. This doesn't necessarily mean our universe isn't special in some way, but it does suggest that the specific rules that govern our reality are not the only possible rules. It links back to the fine-tuning problem we discussed earlier. If there are a vast number of universes with different properties, then the existence of a universe with properties suitable for life like ours becomes less surprising. It's not that our universe was miraculously designed for life, but rather that life can only arise and observe a universe that happens to have the right ingredients. However, directly testing this idea is incredibly challenging. If other universes exist with different physics, they are likely entirely disconnected from ours, making direct observation impossible. Our evidence for this landscape of possibilities and the idea of tunneling between them comes from the mathematical consistency and predictions of theories like string theory and quantum field theory. The challenge is to find predictions from these theories that can be tested within our universe, predictions that might hint at the existence of this larger landscape of possibilities or the nature of the tunneling process that selected our particular spot within it. For example, some theoretical work explores whether the specific pattern of inflation in our universe might contain clues about the landscape from which it tunneled. While still highly theoretical, the possibility that our universe's fundamental physics was determined by a random quantum tunneling event across a vast landscape of potential realities is a powerful concept that challenges our intuition about the uniqueness and inevitability of the laws that govern our existence. One of the most significant challenges facing the standard Big Bang model, and indeed general relativity itself, is the issue of the initial singularity. If you take Einstein's equations and wind the clock backward, you reach a point of infinite density, infinite temperature, and infinite spacetime curvature, the Big Bang singularity. This isn't just a mathematical oddity, it's a signal that our current understanding of physics breaks down completely at this point. The laws of general relativity, which describe gravity and the large-scale structure of the universe, cannot handle infinities. Similarly, if a massive star collapses, it forms a black hole, and general relativity predicts a singularity at its center for the same reasons. Singularities represent a boundary to space-time, a point beyond which we cannot extrapolate using our current theories. They are, in essence, places where physics ceases to make sense. Resolving these singularities is a major goal of theoretical physics, particularly in the search for a theory of quantum gravity. This is precisely where theories involving the universe's first quantum tunneling event offer a potential solution to the initial singularity problem. The core idea is that at the extreme conditions near a singularity, incredibly high densities and tiny scales, classical general relativity must be replaced by a quantum theory of gravity. At these scales, quantum effects, which introduce uncertainty and prevent things from being infinitely precise, become dominant. Just as quantum mechanics prevents an electron from spiraling into the atomic nucleus by describing its position in terms of probabilities and energy levels, a quantum theory of gravity is expected to prevent spacetime from collapsing to an infinitely dense point. Quantum mechanics introduces a fundamental fuzziness or discreteness at the Planck scale, and this quantum nature is thought to smooth out the infinities predicted by classical general relativity. Therefore, a quantum description of the universe's earliest moments should replace the singularity with something finite and physically meaningful. Quantum tunneling provides a mechanism for this something finite to be the beginning of an expanding universe. Instead of hitting a singularity barrier that cannot be crossed in classical physics, the universe described by quantum mechanics could tunnel through or around this barrier. Imagine the Big Bang singularity not as a brick wall, but as a very steep potential energy hill in the landscape of possible cosmic states. Classically, climbing over an infinitely high hill is impossible. But quantum tunneling allows a system to appear on the other side of a classically impenetrable barrier with a certain probability. In various tunneling models, the universe doesn't start at the singularity. It starts in a state that quantum mechanically tunnels into the expanding phase, bypassing the singularity entirely. Different tunneling models handle the singularity problem in slightly different ways, reflecting the various approaches to quantum gravity. In loop quantum gravity, as discussed earlier, the quantization of spacetime itself resolves the singularity, preventing density from becoming infinite. The Big Bounce scenario involves tunneling through a finite, albeit incredibly dense, state that replaces the classical singularity. In models involving tunneling from a false vacuum, the universe tunnels from one stable state to another, and the singularity is simply not part of the trajectory. The universe appears in an already inflating state that, when traced backward, doesn't reach infinite density due to the nature of the initial vacuum energy. String theory-based models, particularly those involving brane collisions or transitions, also aim to resolve the singularity, replacing it with a high-energy, finite-density interaction between branes from which our universe emerges. In these models, the tunneling event is the non-classical process that allows the transition to occur, avoiding the problematic infinite density point. The key takeaway is that by incorporating quantum mechanics into the description of the universe's origin, tunneling theories replace the problematic singularity with a quantum leap, providing a physically consistent picture of how the universe could emerge from extreme conditions without ever reaching a point where the laws of physics break down. It's a testament to the power of quantum mechanics to describe phenomena that seem impossible in the classical world, extending our understanding to the very edge of time and space. One of the most unsettling implications of quantum mechanics is the fuzzy distinction between observer and observed. Unlike in classical physics, where you can measure a system without significantly changing it, at the quantum level, the act of observation itself can influence the outcome. This leads to mind-bending concepts like wave function collapse, where a quantum system exists in a superposition of multiple possible states until it is measured, at which point it collapses into a single definite state. Now apply this idea to the universe as a whole. Some deeply theoretical and often controversial interpretations of quantum mechanics suggest that the universe itself, being a quantum system, might not have had a definite existence or specific properties until some form of observation occurred. In this context, the universe's first quantum tunneling event isn't just a physical transition. It could be fundamentally linked to the emergence of a classical reality from a quantum potentiality, potentially involving the role of observers, however rudimentary. This is where things get truly speculative and delve into the philosophical underpinnings of quantum mechanics. One line of thinking explores the idea that the universe before tunneling existed in a kind of quantum superposition of all possible initial conditions and states different energy densities, different spacetime geometries, different sets of fundamental constants. It was a realm of pure quantum possibility, a cloud of potential realities. The quantum tunneling event, in this view, wasn't just about physically crossing a barrier. It was the moment this cosmic wave function collapsed, selecting one particular set of initial conditions out of the infinite possibilities. But what triggered this collapse? Some interpretations of quantum mechanics, like the Copenhagen interpretation, suggest that measurement by an observer causes collapse. In the context of the early universe, this raises a profound question. Who or what was the observer that caused the universe's initial state to become definite? Different theories propose possibilities. Some suggest that the universe itself, as it reaches a certain level of complexity, becomes its own observer, or that the interaction between different quantum fields within the nascent universe at the moment of tunneling constitutes a form of self-observation leading to collapse. Another perspective, offered by the many worlds interpretation of quantum mechanics, avoids wave function collapse altogether, suggesting that instead of collapsing, the act of observation or interaction simply causes the universe to split into multiple parallel branches, each representing a different possible outcome. In this view, the quantum tunneling event might not be a collapse into a single reality, but rather the point where the initial quantum superposition of the universe diversified into a multitude of separate universes, each resulting from a different tunneling trajectory or outcome. Our universe would simply be one branch among many, corresponding to a particular tunneling path and a specific set of resulting properties. The connection between the universe's quantum tunneling origin and the observer problem forces us to confront fundamental questions about the nature of reality and measurement. If the universe's initial state was determined by quantum processes involving superposition and potential collapse, does that mean the existence of observers, even future ones, was somehow linked to its very beginning? Some interpretations suggest a form of retrocausality, where events in the future, like the emergence of conscious observers, could somehow influence the outcomes of past quantum events, including the universe's initial tunneling. This is highly speculative and debated, but it highlights the deep philosophical implications of taking quantum mechanics seriously when applied to the cosmos as a whole. While there's no consensus on how the observer problem fully integrates with cosmological tunneling theories, the very notion that the universe's birth required some form of interaction or observation to solidify its state from a quantum superposition is a testament to the mind-bending challenges at the intersection of quantum mechanics and cosmology, suggesting that perhaps reality isn't fully formed until it is, in some sense, perceived or interacted with. Another deeply perplexing puzzle in physics, closely related to the mysteries of black holes, is the information paradox. It asks what happens to the information about the quantum state of matter that falls into a black hole. According to classical general relativity, once something crosses the event horizon, it hits the singularity and is gone forever. If information is truly lost in this process, it violates a fundamental principle of quantum mechanics, which states that information should always be conserved. It can be scrambled or transformed, but never truly destroyed. This conflict between the seemingly absolute loss of information in black holes and the conservation of information in quantum mechanics is the essence of the paradox. As black holes are thought to eventually evaporate through Hawking radiation, the question becomes even sharper. If a black hole evaporates, leaving only thermal radiation, but the original matter had specific properties like spin, charge, and other quantum numbers, where did that information go? The Hawking radiation itself seems to contain none of it. Resolving this paradox is a major goal in the quest for a consistent theory of quantum gravity. This is where the universe's first quantum tunneling event, particularly in models involving black hole cosmology or cyclic universes, potentially offers a new angle on this stubborn problem. As we discussed, some theories suggest that the universe might have emerged from a black hole singularity through quantum tunneling. If this is the case, then the process of tunneling itself could provide a pathway for information to be conserved or somehow transferred. Instead of information being destroyed at the singularity, it might be encoded in the state that tunnels through. Imagine the singularity as a complex, turbulent quantum realm. The information about the matter that has fallen into the black hole is not destroyed there but is somehow processed or transformed within this quantum state. The act of quantum tunneling then allows this processed information to transition into a new form, potentially re-emerging in the nascent universe that tunnels out. It's not that the original particles pop back out, but that the fundamental information they carried is preserved and translates into the properties of the new universe. Different theoretical frameworks propose specific ways in which this information might be handled during a tunneling event from a singularity. In some models inspired by string theory or holographic principles, the information might be encoded on the boundary of the black hole or even subtly woven into the structure of spacetime near the singularity. The quantum tunneling process would then effectively read out or transfer this encoded information from the pre-tunneling state to the post-tunneling state. It's like the universe's birthing through tunneling acts as a cosmic information channel, allowing the data about what fell into the black hole to influence the reality that emerges. For instance, the total entropy of the new universe might be related to the information content of the black hole from which it sprang. In cyclic or bouncing universe models where a collapsing universe ends in a high-density state that then bounces back through quantum tunneling, the information from the previous cycle could be carried through this quantum bounce, influencing the initial conditions of the new expanding phase. The tunneling event becomes the critical juncture where information traverses the impossible barrier of the singularity or the point of maximum compression, ensuring its conservation across cosmic cycles. However, making these ideas mathematically rigorous and demonstrating precisely how information is conserved or transferred through tunneling remains a significant theoretical challenge. The exact degrees of freedom and the mechanism by which information is encoded and translated across such extreme transitions are subjects of active research and debate. It requires a complete and consistent theory of quantum gravity, which we don't yet fully possess. Nevertheless, the prospect that the universe's initial quantum tunneling event might be the key to resolving one of the most profound paradoxes in physics, the black hole information paradox, is a powerful motivator for exploring these theoretical avenues. It suggests a deep connection between the origin of our universe, the nature of black holes, and the fundamental principle of information conservation, painting a picture where the ultimate cosmic mysteries are interwoven, and the bizarre process of quantum tunneling might be the thread that connects them all. The sheer scale of the universe is something that boggles the mind. From the tiny particles that make up atoms to the vast cosmic web of galaxies stretching billions of light years across, the universe is immense. Where did this incredible scale come from? Why is the observable universe approximately 93 billion light years in diameter today? Some fascinating theories propose that the answer to this question is directly linked to the specific parameters and conditions of that very first quantum tunneling event. The way the universe started its existence with a non-classical leap could have fundamentally set its initial size and consequently the scale it would grow to over cosmic time. Think back to the idea of quantum tunneling as the universe transitioning from a pre-tunneling state, perhaps a false vacuum or a state of quantum foam, to the expanding universe we inhabit. This transition involved overcoming or passing through a potential energy barrier. The characteristics of this barrier, its height, its width, the shape of the energy landscape on either side, would directly influence the dynamics of the tunneling process. In quantum mechanics, the probability of tunneling depends on these factors. A higher and wider barrier means a lower probability of tunneling, but if tunneling does occur, the system emerges on the other side with a certain amount of energy and in a specific state. Applied to the universe, the energy released during the tunneling event as the universe transitioned to a lower energy state would be the fuel for its initial expansion. The amount of energy released and the way it was distributed would directly impact how quickly and how much the universe initially expanded. a tunneling event through a very high energy barrier might release a tremendous amount of energy, leading to a very rapid and significant initial expansion, potentially setting a larger initial scale. Conversely, tunneling through a lower barrier might result in less initial energy release and a smaller initial starting size. The geometry of the potential energy landscape itself also plays a crucial role. Imagine a landscape with different valleys representing different possible vacuum states and hills representing energy barriers between them. The specific path the universe took through this landscape during the tunneling event, the shape of the barrier it traversed, would influence the state it arrived in on the other side. This arrival state would have a specific energy density and configuration of quantum fields, which would determine the equation of state of the early universe, essentially, how pressure and energy relate. This equation of state is a key factor in how quickly the universe expands. For example, if the tunneling led to a period dominated by the energy of a scalar field like the inflaton field, it would drive that exponential superluminal expansion known as inflation, which would dramatically increase the universe's size in a tiny fraction of a second. The duration and intensity of this post-tunneling inflationary period, directly influenced by the tunneling outcome, would then determine the initial scale of the observable universe. Different tunneling scenarios might predict different initial sizes based on these factors. A model where the universe tunneled from absolute nothing might lead to a different initial size compared to a model where it tunneled from a pre-existing false vacuum within a larger multiverse. Similarly, a scenario involving brane collisions might predict an initial size related to the scale and dynamics of the colliding branes. The quantum fluctuations present during the tunneling event itself could also introduce variations in the initial size and scale, potentially leading to small regions of the universe having slightly different expansion rates immediately after tunneling. These initial variations in scale, amplified over cosmic history by expansion, could even contribute to the large-scale structure we observe today. The challenge for theorists is to connect the microphysics of the tunneling process, the specific quantum gravity or quantum field theory model describing the energy landscape, and the tunneling dynamics to the macroscopic scale of the universe we observe today. By calculating the expected energy release and post-tunneling expansion dynamics for different theoretical models, they can predict the resulting initial size and compare it to the inferred initial conditions needed to produce the universe we see. It's a complex calculation, but it highlights how intimately the vast scale of the cosmos might be tied to the bizarre quantum mechanical leap that marked its first moment of existence. Let's consider a truly profound question about the universe's form. Why do we experience three large spatial dimensions, not two, not four, but precisely three dimensions of space that we can move freely within, plus one dimension of time? This isn't just a casual observation. The number of dimensions significantly impacts the laws of physics and the potential for complex structures and life to exist. For instance, if gravity operated in 4 spatial dimensions instead of 3, it would follow an inverse cube law instead of the inverse square law, potentially preventing stable planetary orbits. If there were only 2 spatial dimensions, the structure of atoms might be different, possibly preventing the formation of complex molecules like those necessary for life. So, the number of dimensions is a fundamental property of our universe, and some theories suggest that the universe's very first quantum tunneling event was the process that determined this number. This idea often arises in theoretical frameworks that propose the existence of higher dimensions beyond the 3 spatial ones we readily perceive. String theory, which we touched on earlier, typically requires 10 or 11 spacetime dimensions for mathematical consistency. Similarly, some other theoretical models, including those in quantum gravity, might involve extra dimensions. If these extra dimensions exist, why don't we see them? The common explanation is that these extra dimensions are compactified or curled up to an incredibly small size, far too small to be directly observable. Imagine a garden hose. From a distance, it looks like a one-dimensional line, but up close, you see it has a second, curled-up dimension around its circumference. Similarly, the extra dimensions are thought to be curled up into tiny, compact spaces at every point in our familiar three large dimensions. The radius of these compactified dimensions is thought to be around the Planck length, that same incredibly small scale where quantum gravity effects become dominant. Now, how does quantum tunneling play a role in this dimensional picture? Theories linking tunneling to the number of dimensions propose that the universe, in its pre-tunneling state, might have existed in a higher dimensional space with perhaps 9 or 10 spatial dimensions. The quantum tunneling event, in this context, wasn't just about transitioning to a lower energy state or emerging from a singularity. It was a process that somehow triggered the compactification of these extra dimensions, leaving only 3 large, extended spatial dimensions and one time dimension to expand into the universe we inhabit. Imagine the pre-tunneling state as a higher dimensional configuration. The tunneling process was a transition to a different configuration, one where the dynamics favored 3 dimensions expanding to macroscopic size while the others were forced to curl up into tiny, unobservable spaces. The energy and dynamics of the tunneling could have provided the impetus for this dimensional reduction, much like a phase transition where the fundamental structure of the system changes. The specific way the universe tunneled out of its initial state could have determined which 3 dimensions became large and which ones were compactified, and perhaps even the size and shape of those curled-up extra dimensions. Different models within string theory and other higher dimensional frameworks offer specific mechanisms for how this dimensional compactification could be linked to a tunneling event. For example, in some brain world scenarios, our universe is a brain embedded in a higher dimensional bulk space. The tunneling event could be a process where this brain transitions to a state where 3 spatial dimensions are free to expand along the brain, while the extra dimensions are transverse to the brain and remain confined to a tiny, curled-up space. The dynamics of the brain itself and its interaction with the bulk space during the tunneling would dictate this outcome. In other models, the quantum tunneling could involve a change in the configuration or topology of the extra dimensions, causing them to shrink down to their compactified size as the universe transitions to its post-tunneling state. The energy released by this compactification process could even contribute to the initial energy density that drives the universe's early expansion. The challenge is to develop theoretical models where the probability of tunneling into a state with 3 large spatial dimensions is significantly higher than tunneling into a state with a different number of dimensions, providing a natural explanation for why our universe has the dimensionality it does. While directly observing these extra dimensions or the tunneling event that might have caused their compactification is currently impossible, the theoretical consistency and explanatory power of these models in addressing fundamental questions about the universe's structure keep this idea at the forefront of research in theoretical cosmology and particle physics. It suggests that the number of dimensions we live in is not a preordained given, but a contingent outcome of the universe's bizarre quantum mechanical birth. The universe's first quantum tunneling event wasn't just about creating space and time. It also involved energy levels and densities so extreme that they could have given rise to forms of matter unlike anything we see in the universe today. Imagine conditions far, far hotter and denser than the core of the Sun, or even the heart of a neutron star. These are the kinds of environments we're talking about when considering the moments immediately following the universe's non-classical birth. Some theories suggest that at these incredibly high energies, matter wouldn't have existed in the familiar forms of protons, neutrons, and electrons. Instead, it could have existed in exotic, fleeting states, theoretical forms of matter that are only possible under such extreme conditions. One well-known example is the quark-gluon plasma. While not strictly hypothetical, as it's been briefly created in particle accelerators like the Large Hadron Collider, It's an exotic state where quarks and gluons, the fundamental building blocks of protons and neutrons, are not confined within particles but exist as a superhot, dense fluid. This plasma is thought to have filled the universe for the first few microseconds after the Big Bang, as it cooled from its initial incredibly high temperature. The connection to quantum tunneling is that the energy released during the tunneling event itself, as the universe transitioned to a lower energy state, would have been enormous. This sudden injection of energy would have heated the nascent universe to temperatures where even fundamental particles couldn't hold together in their usual configurations. The specific energy scale of the tunneling and the dynamics of how that energy was distributed would directly influence how hot and dense the universe became immediately after its birth. If the tunneling occurred at a very high energy, it would have resulted in a universe filled with this superhot quark-gluon plasma. As the universe then expanded and cooled, this plasma would have undergone a phase transition, condensing into the protons and neutrons that eventually formed atomic nuclei. The tunneling event, in this view, wasn't just the starting gun for the universe's expansion. It was the furnace that forged the initial state of matter. But the possibilities might be even stranger. Some theories go beyond the standard model of particle physics and propose the existence of even more fundamental particles. One such concept is preons, hypothetical subatomic particles that could be the building blocks of quarks and leptons like electrons. If preons exist, they would only manifest at energies far higher than we can currently probe, perhaps energies reached only during the universe's first moments. The extreme energy densities achieved during or immediately after the quantum tunneling event could have briefly created a preon plasma, a state where these ultimate building blocks existed freely before combining to form quarks and leptons as the universe cooled further. This would be a level of reality even more fundamental than the one described by the standard model, fleetingly present at the moment of cosmic creation before receding into the realm of theoretical speculation as the universe quickly expanded and cooled below the energy threshold required to sustain them. The tunneling event would be the unique window in cosmic history where such incredibly fundamental particles might have existed as a distinct state of matter. Finding direct evidence for these exotic states, especially hypothetical ones like preon plasma, is incredibly difficult because they existed for such a short time and at such extreme energies. However, scientists look for indirect signatures. The way the quark-gluon plasma cooled and condensed into protons and neutrons, for example, could have left subtle imprints on the distribution of matter in the early universe or on the production rates of certain light elements during nucleosynthesis, the process where the first atomic nuclei formed. Similarly, if preons existed, the way they combined into quarks and leptons might have left subtle deviations from the predictions of the standard model that could potentially be detected in future high-precision particle physics experiments or cosmological observations. The search for these potential echoes of exotic matter states created by the universe's initial quantum tunneling is a quest to understand the composition of reality at its most fundamental level, seeking clues about the incredibly strange and energetic conditions that must have existed at the very moment our universe took its first impossible breath. Consider a fundamental question that arises when we think about the universe's origin. Could there be a smallest possible size for reality? It might seem counterintuitive. Surely you can always divide something into smaller and smaller pieces. But just as energy and matter come in discrete packets at the quantum level, there's a powerful idea in physics that space and time themselves might have a minimum scale, a smallest possible unit beyond which they lose their familiar properties. This is the concept of the Planck scale, named after Max Planck, one of the founders of quantum mechanics. The Planck length, approximately 1.6 times 10 to the power of -35 meters, is thought to be the scale at which quantum effects of gravity become dominant, and the very fabric of spacetime is expected to behave in ways we can barely imagine. At or below this scale, our current understanding of spacetime as a smooth, continuous manifold breaks down, It's where the quest for a theory of quantum gravity becomes essential, as classical general relativity is insufficient to describe physics at such tiny distances and enormous energy densities. This brings us directly to theories connecting the universe's first quantum tunneling event to this fundamental minimum size. If there is a minimum physical scale at which spacetime can exist in a meaningful way, what does that mean for the beginning of the universe? In classical cosmology, the Big Bang singularity predicts the universe started from a point of zero size, infinitely dense. But a point of zero size is smaller than any conceivable minimum length, including the Planck length. This is another way of framing the singularity problem we discussed earlier. It's a point where the physics we know ceases to apply, perhaps because we've gone below the minimum meaningful scale of spacetime. Theories involving the universe's initial quantum tunneling propose that the pre-tunneling state, or the state from which the universe emerged, was either at or below this Planck scale, and the tunneling was a transition that allowed it to jump out of this ultra-microscopic realm into a state above the minimum size where spacetime could expand. Imagine the Planck length as a fundamental barrier. Classically, if the universe were to somehow exist at a size below this Planck length, it would be trapped in a state where our familiar physics doesn't work, potentially a singularity or some other undefined state. But quantum tunneling offers a way to bypass this barrier. The universe, in this ultra-tiny, pre-Planckian state, could quantum mechanically tunnel through the barrier of the minimum size, appearing on the other side in a state large enough for spacetime to be well-defined and for expansion to begin. This tunneling would not be a classical expansion from a point. It would be a non-classical leap from a realm smaller than the fundamental scale to a state significantly above it. The minimum size isn't just a limit on observation. It's a potential boundary in the energy landscape of the universe itself, and tunneling is the only known mechanism for crossing such a classically forbidden region. Different models of quantum gravity offer variations on this theme. In loop quantum gravity, as explored earlier, the quantization of spacetime naturally introduces a minimum length scale, effectively the size of the fundamental loops. The bouncing universe scenario in LQG can be interpreted as the universe contracting to near the Planck size, where quantum effects become repulsive, and then quantum tunneling through that minimum size boundary into a new expanding phase. The universe never hits zero size. It reaches a finite Planck-scale density and then tunnels through. In other theoretical frameworks, the pre-tunneling state might be described as a Planck epoch foam, a turbulent state of spacetime at the Planck scale. The tunneling event is then seen as the universe emerging from a region or configuration within this foam, transitioning to a smoother, larger-scale state capable of sustaining expansion. The energy released during this transition from the tiny, ultra-dense state above the minimum scale would fuel the subsequent early expansion, potentially inflation. The concept of the universe quantum tunneling from a state smaller than the minimum possible size is a powerful way to address the singularity problem and provide a physically meaningful starting point for cosmic evolution, suggesting that the universe's first impossible jump was a leap across the threshold of the smallest possible reality. Let's explore a truly mind-bending concept that pops up when physicists talk about the universe's beginning and quantum tunneling, the idea of imaginary time. Now, if you hear imaginary time, you might think of something made up or not real, and in a way, that's part of it. In mathematics, imaginary numbers are those that involve the square root of -1, denoted by the letter I. While they might seem abstract, imaginary numbers are incredibly useful tools in many areas of physics, helping to describe phenomena that are difficult to handle with real numbers alone. When we talk about imaginary time in the context of cosmology and quantum tunneling, it's not that time itself literally becomes imaginary. Instead, it's a mathematical trick or a way of formulating the problem that simplifies the calculations and allows us to describe processes that are fundamentally non-classical and occur in realms beyond our everyday experience of spacetime. The concept of imaginary time often appears when physicists use a mathematical technique called a Wick rotation. This involves substituting real time, which we usually denote by t, with imaginary time, often related to I times an equivalent spatial coordinate or another form of parameter. This transformation has a remarkable effect. It changes the mathematical description of spacetime from the kind we experience, known as Lorentzian spacetime, which has one time dimension and 3 spatial dimensions with a particular mathematical signature, to what's called Euclidean spacetime, which has 4 spatial dimensions with a different mathematical signature, similar to regular dimensional space but with an extra dimension. In Euclidean spacetime, there's no distinction between space and time. They are all treated as spatial dimensions. This mathematical shift from Lorentzian to Euclidean is particularly useful when describing quantum processes that occur under the barrier, in regions that are classically forbidden, like the tunneling process itself. Think back to the idea of quantum tunneling. Classically, a particle or the universe itself is trapped on one side of an energy barrier. To describe how it gets to the other side quantum mechanically, physicists often use techniques that involve looking at the probability of the system existing in the classically forbidden region. This is where the mathematical power of using imaginary time comes in. Calculations using imaginary time can describe this transition from a non-classical, often Euclidean-like region on one side of the barrier, through the barrier itself, to the classical Lorentzian spacetime we inhabit on the other side. It provides a mathematical bridge between a state where our usual concepts of space and time might not apply, the pre-tunneling state or the state within the barrier, and the familiar spacetime of our universe. It's not that the universe existed in imaginary time before tunneling, but rather that imaginary time is a mathematical tool that helps us calculate the probability of the tunneling event happening and the properties of the resulting universe in real Lorentzian time. One of the most famous proponents of using imaginary time in cosmology, particularly in relation to the universe's origin, was Stephen Hawking. In his work with Jim Hartle, they developed the no-boundary proposal for the universe. This proposal suggests that if you describe the universe's initial state using imaginary time, it would be like the South Pole on the surface of a globe. Just as you can't go any further south than the South Pole, there's no boundary beyond it in this proposal. The universe's history, described in imaginary time, has no beginning point or boundary in the same way that the South Pole is the southernmost point without being a boundary edge. The idea is that the universe's history extends into a realm described by Euclidean spacetime, using imaginary time, before transitioning to the Lorentzian spacetime of the expanding universe. The transition from this Euclidean region to the Lorentzian region can be mathematically described as a quantum tunneling process. Stephen Hawking famously suggested that this approach, using imaginary time, could mean that the universe didn't need a specific starting point or cause in the classical sense. Its initial state was simply like the South Pole, a smooth origin without a boundary. This mathematical framework provided a way to describe the probability of the universe coming into existence with its specific properties through a quantum process, essentially tunneling from a state that, when described in imaginary time, had no singular beginning. While the concept of imaginary time in cosmology is a complex mathematical tool, and its interpretation in terms of physical reality is debated, its use in describing the universe's initial quantum tunneling event, particularly in the context of proposals like the no-boundary hypothesis, offers a powerful way to think about origins without needing a classical starting point, providing probabilities for the universe's birth from a non-classical realm. If the universe truly sprang into existence through a quantum tunneling event, it begs a fundamental question: how likely was that event? Was it an incredibly improbable cosmic fluke, or a more predictable outcome given the conditions of the pre-tunneling state? Understanding the statistical probability of such a monumental tunneling event occurring is a key aspect of these theories, and it depends heavily on the specific parameters of the theoretical energy landscape involved. In quantum mechanics, the probability of a particle tunneling through a barrier is governed by factors like the height and width of the potential energy barrier and the difference in energy between the state before and after tunneling. A higher and wider barrier makes tunneling less likely, while a lower and narrower one increases the probability. Applied to the universe, the energy landscape could represent different possible vacuum states or configurations of spacetime, and the barrier is whatever prevents a classical transition between them. The energy difference between the pre-tunneling state and the state of our universe after tunneling would be crucial. A larger energy difference often increases the probability of tunneling to the lower state. These factors the shape of the energy landscape. The dimensions and height of the barrier are determined by the specific details of the fundamental physics in play at those extreme scales, such as the properties of the quantum fields or the dynamics of branes in higher dimensional models. Different theoretical frameworks for the early universe will predict different energy landscapes and thus different probabilities for quantum tunneling. For example, in a false vacuum tunneling scenario, the shape of the potential energy curve for the scalar field determines the barrier. A very stable false vacuum implies a high and wide barrier, making tunneling a rare event. Conversely, a very unstable false vacuum would have a lower, narrower barrier, increasing the tunneling rate. The complexity comes in calculating these probabilities in the context of the entire universe, not just a single particle. It involves considering the quantum state of the entire cosmos and the dynamics of quantum gravity or the relevant fundamental fields. The calculations are often complex and rely on approximations and specific theoretical models. The seemingly low probability for a single, isolated quantum tunneling event to produce a universe like ours, with all its specific properties and fine-tuning, might lead one to believe our existence is unbelievably improbable. However, this is where the concept of a vast cosmic landscape or multiverse, often arising from theories like eternal inflation, becomes relevant again. As we discussed, eternal inflation suggests that inflation, once started, continues indefinitely in some regions, perpetually spawning new bubble universes as it ends in others. If this process is indeed eternal and produces an infinite or near-infinite number of bubble universes, each potentially born from a quantum tunneling event from the inflating background, then even incredibly improbable events are bound to happen somewhere within this vast ensemble. Imagine flipping a coin an infinite number of times. Eventually, you're going to get a very long string of heads, however unlikely it is in a short series. Similarly, if tunneling events are constantly happening across an immense landscape of possibilities, then it becomes statistically likely that at least some of these events will produce universes with the specific parameters and initial conditions necessary for complexity and life to arise like our own. This brings us back strongly to the anthropic principle, which gains significant explanatory power in this context. If our universe is just one outcome among countless possible universes generated by quantum tunneling in a vast landscape, then the reason we observe the universe to have the specific, seemingly fine-tuned properties it does is simply because those properties are a prerequisite for observers like us to exist. We couldn't possibly find ourselves in one of the vast majority of universes where the tunneling event led to physical laws or initial conditions hostile to life. Those universes would be sterile. Our existence acts as a selection bias. While the probability of a random tunneling event producing our specific universe with our specific properties might be incredibly low when viewed in isolation, when considering an infinite or vast landscape where all possible outcomes occur with some non-zero probability, it becomes statistically unsurprising that a universe suitable for life exists and we are in it. The quantum tunneling event, in this view, isn't a single, miraculous occurrence against impossible odds. but rather a common mode of cosmic generation within a larger, perhaps infinite, reality, and our presence within our particular universe is a consequence of both the vastness of possibilities created by tunneling and the simple fact that we can only observe realities that allow observers. It's a perspective that uses the probabilistic nature of quantum tunneling on a cosmic scale to address the apparent fine-tuning of our universe, suggesting our existence is less a miracle and more a statistical inevitability within a grander cosmic lottery initiated by quantum leaps. Thinking about the universe's first quantum tunneling event naturally leads to a perhaps more unsettling question: could it happen again? If the universe tunneled into existence, is it possible that it could, at some point in the far future, tunnel into a different state? This isn't just idle speculation. It's a serious theoretical possibility explored by physicists, particularly in the context of vacuum stability and the potential for future phase transitions. The universe we inhabit is believed to be in what we call a vacuum state, the lowest possible energy configuration for the fundamental fields that permeate spacetime. However, as we discussed earlier with the false vacuum concept, it's possible for a system to be in a metastable state, a temporary energy minimum that isn't the absolute lowest possible energy state. If our universe is currently in such a metastable false vacuum, it raises the chilling possibility that it could, at some point, quantum tunnel to a lower, more stable true vacuum state. This hypothetical event is known as vacuum decay, and it's often described as the ultimate cosmic catastrophe. If our universe were to tunnel to a lower energy vacuum, it wouldn't be a gentle transition. It would likely start in a small region of spacetime, a bubble of the new, lower energy vacuum spontaneously appearing due to quantum tunneling. This bubble would then expand rapidly at nearly the speed of light, converting the false vacuum of our universe into the true vacuum within its boundary. As the bubble expands, it would release the energy difference between the false and true vacuum states, creating a colossal wave of energy. Within this expanding bubble of the true vacuum, the fundamental physical constants, things like the mass of the electron, the strength of the electromagnetic force, or the force of gravity, could be completely different. Particles might have different masses, forcing might interact differently, or some particles might not even exist in the new vacuum. Anything caught within the expanding bubble of the true vacuum would be instantly and fundamentally altered. Atoms as we know them might cease to exist, chemical bonds would break down, and the very fabric of space and time could be reconfigured. From the perspective of anyone outside the expanding bubble, they would simply see an ever-approaching wall of destruction, beyond which their reality is utterly unrecognizable or simply annihilated. The likelihood of this terrifying scenario depends on how stable our current vacuum state actually is. Particle physics experiments, particularly those involving the Higgs boson at the Large Hadron Collider, provide crucial data that helps us assess the stability of our vacuum. The mass of the Higgs boson and the masses of other fundamental particles are inputs into calculations that determine the shape of the Higgs field's potential energy landscape. Based on the currently measured values, it appears that our vacuum state lies in a subtle position in this landscape. Some interpretations of the data suggest that our vacuum might not be perfectly stable, but is instead metastable, perched on a very gentle slope that, in the far, far future, could allow for tunneling to a lower energy state. However, there are uncertainties in these calculations, particularly when extrapolating to the incredibly high energies relevant for vacuum stability, and other particles and fields beyond the standard model could influence the picture. The theoretical possibility of vacuum decay via quantum tunneling remains, highlighting a potential fragility of our cosmic existence rooted in the deepest quantum nature of reality. Beyond the potential for our entire universe to tunnel to a different vacuum state, some theories, particularly those involving eternal inflation and the multiverse, suggest that new bubble universes could spontaneously nucleate and appear within our own spacetime through quantum tunneling. This is a different kind of future tunneling event. Instead of our vacuum decaying, it's possible that due to quantum fluctuations within our existing spacetime, a small region could tunnel into a different vacuum state that then expands rapidly, forming a new universe potentially disconnected or only subtly interacting with ours. While such a new universe would likely expand away from us at superluminal speeds, a theoretical possibility exists that if such a bubble nucleated sufficiently close to us and expanded towards us, it could collide with our universe, creating detectable imprints or even causing localized destruction. These future tunneling events, whether they involve the decay of our vacuum or the spontaneous creation of new bubbles within it, are a chilling reminder that the quantum processes that might have birthed our universe could also play a role in its ultimate fate, adding another layer of profound uncertainty to our understanding of cosmic evolution and the long-term stability of the reality we inhabit. It forces us to consider that even billions of years after its initial tunneling leap, the universe might remain susceptible to the strange and powerful dictates of quantum mechanics. We've journeyed through a landscape of truly mind-bending ideas, exploring 30 different theories about that incredible, impossible moment, the universe's very first quantum tunneling event. We've seen how this fundamental quantum phenomenon, the ability to pass through barriers that should be impenetrable, could be the key to unlocking the deepest secrets of our cosmic origins. We started with the inflationary tunneling model, suggesting the universe leaped into its rapid expansion from a trapped state. Then we plunged into the radical idea of tunneling from nothing, a spontaneous quantum emergence from absolute void. We explored the possibility of our universe being just one bubble in a vast multiverse, born from a tunneling event within a larger cosmic structure. We delved into the bizarre realm of spacetime foam and the concept of a universe tunneling out of this turbulent quantum realm, and considered the Big Bounce scenario in loop quantum gravity, where a contracting universe tunnels through a quantum barrier instead of hitting a singularity. We examined how tunneling from a false vacuum could have fueled the universe's initial inflation and pondered the chilling possibility of future vacuum decay. We've seen theories suggesting that this initial quantum leap established the arrow of time, determined the universe's fine-tuned constants within a vast landscape of possibilities, and even set the stage for the imbalance between matter and antimatter. We've connected tunneling to the mystery of dark energy, explored the imprints it might have left on the cosmic microwave background radiation as the seeds of structure, and linked it to the unifying vision of grand unified theories at extreme energies. We bravely considered the mind-bending idea that the universe's birth might be tied to the observer problem in quantum mechanics, and that it could have happened within hidden sectors of reality. We've explored theoretical connections to quantum entanglement entropy as a descriptor of the pre-tunneling state, pondered how tunneling might have determined the number of spatial dimensions we inhabit, and even touched on the exotic forms of matter that could have briefly existed in the extreme heat of that initial transition. We saw how tunneling offers a potential resolution to the problematic initial singularity in classical cosmology, and glimpsed the mathematical power of imaginary time in describing these non-classical origins. Finally, we considered the statistical probability of such an event and the potential for future tunneling events, highlighting the universe's ongoing connection to the quantum realm. Each of these theories, while still highly speculative and often pushing the boundaries of our current understanding, represents humanity's persistent and passionate quest to comprehend the most fundamental questions. Where did we come from? Why is the universe the way it is, and are we alone in the cosmos? They remind us that the reality we inhabit, seemingly so solid and predictable on our everyday scales, might have sprung from a realm of quantum weirdness and impossibility. They challenge our classical intuitions about beginnings, causality, and the very nature of spacetime. While direct observational evidence for many of these tunneling scenarios remains elusive, the continued development of theoretical frameworks like quantum gravity and the increasing precision of cosmological observations, like those of the cosmic microwave background and large-scale structure, offer hope that we might one day find concrete clues about the universe's initial quantum leap. The universe is vast, and the unknown is even vaster. The idea of its first quantum tunneling event is a powerful reminder of how much there is yet to discover, how strange and beautiful reality might be at its most fundamental level. It encourages us to keep asking questions, to keep exploring the furthest reaches of physics and cosmology, and to remain open to possibilities that might seem impossible today. The journey to understand our cosmic origins is far from over, and the potential for future discoveries to shed more light on this fundamental moment, to potentially confirm one of these incredible tunneling theories, is a thrilling prospect. It leaves us with a profound sense of wonder, looking out at the night sky and contemplating the unimaginable quantum forces that might have set it all in motion.